Good morning, good afternoon to all. Welcome to the first Canadian Photonics Online Meetup. My name is Dr. Orad Reshef. I'm a postdoc at the University of Ottawa. Thank you so much for taking time out of your week to come here and spend your Friday with us. It is really exciting to see the number of people on the stream rising and seeing some people already running around in our conference center on GatherTown. It's pretty incredible. Over 300 people have registered. That's funny, I hear my own stream. Okay, I closed it. There are over 300 people that have registered from over 30 institutions across the country, and we're expecting to have a very lively event, both in this stream right here and in the conference center. Let me begin by acknowledging the generous support of the CRPUO, which is the Center for Research in Photonics at the University of Ottawa, and JCEP, which is the Joint Center for Extreme Photonics from U Ottawa and the NRC. They have combined to foot the bill for this entire conference out of pocket. So everything you see here, from the stream to the career fair to the poster session, all of that stuff is entirely free for you guys and free to all participants thanks to them. You can learn more about these organizations at photonics.uottawa.ca and at extremephotonics.com, respectively. We also acknowledge support from CMC Microsystems, Science Atlantic, Nano Canada, and all sorts of student chapters from the INRS, l'École Polytechnique Montréal, from U Ottawa and from Laval for, among other things, promoting our conference and helping with our translations for the website. canPOM is affiliated with the Photonics Online Meetup. They're an organization devoted to increasing accessibility of conference attendance and to high-quality photonics research. All POM events are entirely free and are entirely run by volunteers. I want to say that the next flagship POM event is going to be in mid-January. It's free to register. And for more information on POM, you can go to photonicsonlinemeetup.org. So now I'm going to introduce my wonderful co-chair, Kate Fenwick. She's a graduate student here at University of Ottawa and at the NRC, and she's going to tell you about the activities of the day. Take it away, Kate.
Wonderful. Thank you, Orat. We have an exciting day planned for everybody today with 4 incredible research groups from all corners of our great country. Professor Joyce Poon from the University of Toronto is here to talk about silicon photonics. Professor Ebrahim Karimi from the University of Ottawa is here to discuss quantum optics using structured light. Professor Christa Brosseau from St. Mary's University in Halifax will be presenting her group's research on plasmonics. And Professor Frank Hegmann from the University of Alberta in Edmonton will talk about using terahertz techniques in the nanoscale. In the middle of the day, we feature a discussion panel with distinguished members from industry called Where to Go After Finishing Your Degree in Physics. Our entire program can be viewed both in English and in French at our website, which is canpom.photonicsonlinemeetup.org. Throughout the day, you will be able to walk around our custom conference center with your very own personalized avatar. Pretty cool. There's an auditorium where you can grab a seat with your colleagues and tune into this very stream with no delay. Starting in the morning, we will be featuring a poster session with almost 40 posters from students across our country. After lunch, we will open up our career fair, which actually has over 20 booths from different employers, organizations, university administration, and even some PIs looking to talk to students like you. And finally, capping off our event will be a real virtual conference dinner, the likes of which you have yet to see in a virtual conference. So please stay tuned for that at the end of the day. It should be very fun. And finally, we hope you enjoy our event. Once it's over, we'll be sending out a short survey. Please fill it in to let us know what you think so that we can learn how to improve upon this event in the coming years. And finally, if you have any suggestions or would like to volunteer, we would love to hear from you. And with that, I am going to pass it off to our other organizing committee member, Peter. Peter will be introducing Joyce Poon and her research group, who is our first research showcase session. So with that, I will pass it off to Peter.
Thank you very much, Kate. It's my pleasure to introduce the first of our 4 research showcases. Professor Joyce Poon is director of the Max Planck Institute of Microstructure Physics, professor of electrical and computer engineering at the University of Toronto, and an honorary professor in the Faculty of Electrical Engineering and Computer Science at the Technical University of Berlin. Her group specializes in integrated photonics on silicon and the development of devices for applications in neurotechnology. Among her works, many distinctions she has received the Ontario Ministry of Research and Innovation Award. She's a two-time recipient of the IBM Faculty Award. She's been named one of the world's top 35 IT innovators under 35 by the MIT Technology Review. And she is a fellow of the Optical Society, where she will be director at large from this January. Before I turn the mic over to Professor Poon and her team, I just want to remind our audience to post any questions we may have over on YouTube if you're joining us through there, or by private messaging canPOM in Gabbertown, and we'll address them after each speaker. Thank you very much for joining us, Professor Poon. Please go ahead.
So hi everyone, and thank you to Aura, Kate, Peter, and all the other students who organized, students and postdocs who organized this event. I think it's really important for people to come together at this really difficult time. So I hope also to answer some of your questions. So let me also share my screen here. Let's see, presentation. Hope this is working. So today, actually joining me today are two PhD students in my group. One is Tori Thyssen, and he will speak next, and then followed by Fred Chen. They're both students at University of Toronto. Tori is completing his thesis at University of Toronto, and Fred is actually completing his research in Germany, and he's in Germany at this moment at the Max Planck Institute for Microstructure Physics. So I'll kick off by telling you a bit about our research and our research group, and if you can also understand through this our sort of transatlantic research activity, how we manage to do research in both sides of the ocean. First of all, I'd like to tell you a bit about the motivation for our work. As many of you know, in fact, Moore's Law is ending. So Moore's Law, which has really been the engine to power the information age for the last half century or so, has in fact come to a halt. The transistors are no longer getting smaller. For the past 5 to 10 years. The names are still changing, so it sounds like the transistors are getting smaller, but physically they are not anymore. And it's just really difficult to make transistors smaller and smaller. What could be next? And we are still very interested in advancing computing technology, because computers, we think, are very important for solving very big problems in our society, for example, healthcare, transportation, sustainability. These types of questions really require very powerful computers. And so for very large scale systems, we see some problems today, computing systems face today would be in power consumption and in delay, how to compute faster and so on. And yet at the same time, there are also lots of opportunities for very, very small computers. So computers are not just, the big mega data center systems, but, they're also very, very much integral part of our lives today. So, what could be next beyond the smartphone or the smartwatch, and how can human really interface with computers? So we see some new opportunities. So for the future, you can imagine that if we want to solve problems that large-scale systems face today, we can consider new types of computing architectures that could leverage from very energy-efficient communication that could happen, new ways of accelerating computation, maybe even fundamentally new ways of doing computing itself. So for example, brain-inspired computing, so neuromorphic computing, but also been quantum computing in the same bucket here. And then on this other extreme scale for computers, for these very small portable types of computers, we can imagine new form factors for in the future. So wearable, for example, very lightweight wearable displays, so that we can have these glasses that are not so ugly and heavy. That could be a future for for computers. And also ultimately, perhaps computers would even be integrated within us. So can we imagine computing interfaces directly that are directly interfaced with the brain? And so this research mission of creating devices and systems that enable future computers is what drives our research. And I became a director at the Max Planck Institute in 2018 and full-time last year in 2019, but I'm still a professor at U of T in Toronto. And the Max Planck Society and the Max Planck Institutes that are in the society, they do not offer academic degrees. So they're just purely research institutes. So then students can get the degrees actually technically anywhere in the world. And they can conduct their research at the research institute. And this is how some of my PhD students are in fact based in Germany at the moment and carrying out their research at the MPI instead of on campus at U of T. But at U of T, we still have research activity and some labs. And in U of T, in Toronto, we've focused a lot on hybrid 3.5 on silicon. So the 3.5, a 3.5 compound semiconductor on silicon integrated photonics. And this is a very near-term technology to enable very efficient data comm. And Tori will talk more about that next. In the MPI, we are able to take slightly longer term view on projects. So we are interested in developing visible light integrated photonic circuitry. And this is all done in silicon still. And Fred will talk about its application for neurotechnology. We also applying that to make microchips that could have display applications. We also worked on phase change materials to enable neuromorphic computing. And also do conventional silicon photonics research for hardware accelerators. I won't have time to talk about this topic today, and I'll let Tori and Fred go into more depth about these two topics, and I'll just talk briefly also about the phase change materials. So to give a little bit more context for the work, so we work a lot with silicon substrates, but in fact, in my group, we work with foundries a lot. So we go into this mode of foundry silicon photonics. And the idea of foundry silicon photonics is to actually use the manufacturing capability in CMOS to produce photonic chips. And so a lot of the fabrication of our photonic devices and of the photonic circuits are not done in-house, but in fact, they are done at semiconductor foundries. We work with a lot of R&D scale foundries like AMF in Singapore. We partner with a lot. We work with CA-Leti in France quite a bit. And of course, there are now commercial foundries that are producing products using silicon photonics technology. So Intel, ST Microelectronics, TSMC all have silicon photonic fabrication runs in their facilities. And so in doing it work this way, then there's a very heavy focus in the group of doing simulation, doing a lot of design, and then also working with the foundries to understand the limitations. So we do not work with we do not always work with available multi-project wafer runs. We actually work with the foundries to develop new types of photonic platforms that, in the future could become a multi-project wafer run for others too. But there's a lot of co-development with the foundries. And then the foundries make the silicon photonic chips and our devices for us, and they realized often on 8-inch or 12-inch wafer, and then the wafers are shipped back to us, and then we focus a lot of effort on measurements as well. The typical silicon photonic platform cross-section looks like this. It has a silicon layer that is used to form waveguides, and there's doping available to form modulators. There you can deposit germanium on it to make a photodetector. And all of this is surrounded by oxide. There's the underlit cladding here. It's called buried oxide layer, and then it all sits on a silicon substrate. And this is what you could find in these foundries. Today's CMC microsystems also offer fabrication runs, so it's quite accessible. And this platform is very good for telecommunication wavelengths, so near 1310 nanometer or 1550 nanometer. And you can certainly be very creative in this space. Of course, one crucial block that is missing are the lasers. So the lasers silicon is not a good light emitter. So how will the lasers be integrated? And that is the subject of Tori's work. So I'll let him talk more about how we do it and the research that goes on in my group on that topic. And then on the visible light spectrum work, so in this new direction, so we're moving away from the telecom wavelengths and into much shorter wavelengths. And of course, silicon absorbs light in the visible spectrum. So our efforts have really concentrated on using silicon nitride waveguides to route the light. And we're developing more complex platforms with silicon nitride waveguides. That work is still ongoing. So last year, after a number of years of development with Advanced Micro Foundry in Singapore, we achieved very low loss, relatively low loss waveguides in the visible spectrum. So cross section is very simple. It just looks like this with a thin layer of silicon nitride waveguide, surrounded by an oxide cladding on a silicon substrate, and we were able to achieve losses of about, as you can see, sort of 4 or 5 dB per centimeter single mode waveguides in the blue wavelengths. So this is, in fact, a record low loss at the short wavelengths. And one application that we have here is to use the technology, as Fred will explain in even greater depth, to make implantable devices that are meant to go into the brain. And in the video that you just saw, it froze or it stopped, and I'm not sure how to restart it. Oh, there we go. In the field of neurobiology, optical technology has really been revolutionary in the study of brain activity. The neurons now can be genetically modified so that you can actually image their fluorescence when there's activity. So for the first time, the neuroscientists are able to actually capture videos, volumetric videos of neuroactivity. There could also be opportunities to also modify the neurons using optogenetic techniques so that you can, in fact, use light to turn neurons on and off. And so now, again, neurobiologists are doing research in which they would implant a fiber into a mouse to turn on and off specific populations of neurons with light. So let's see. And so what we are doing is to use the Silicon Foundry technology to create implantable chips that can bring light directly into the animal without necessarily injecting light from a microscope or even a fiber. And again, through a number of years of development with AMF, Advanced Micro Foundry, we've developed a process of making these neurophotonic probes. And these probes are done on very thin silicon wafers. The entire wafer has to be thinned down to less than 100 microns so that they can actually be implanted into the tissue. But because we use this foundry process, we are able to then, in fact, achieve these probes on 8-inch wafers, and then you can get more than 1,600 probes in a single wafer. Here are some microscope images of these probes. They have these thin needles, and these needles are actually the part that penetrate into tissue, and they're gratings on the shanks here so that light can be emitted. And we also have a way of addressing these greetings on the shanks. And again, I'll let Fred talk more about the applications and the research that we have with the neurophotonic probes. And then the final research topic that I'd like to get into is our work on phase change material devices. So this is a little bit different in tone compared to the other work. So here we actually do fabricate devices ourselves. In this work, we explore what we can do using materials that can exhibit phase change. And a material that we've been looking at is vanadium dioxide, or VO2. So this material can, in fact, transition from being an insulator to metal at the ambient temperatures, near ambient temperatures, around 67 degrees Celsius. You can also get this phase change going by shining light, by ion gating as well. So it's not just thermal. You can also apply a current or voltage. And what we recently discovered was something very interesting, and it was an accidental discovery of sorts in the lab. So we discovered that this VO2 material can in fact function as a non-volatile memory. So I'll just briefly tell you about this observation and this discovery. It's very interesting. So Young Ho and Dave, the postdoc students on the project, they made the VO2 micro wires with 2 electrodes that you see on the right-hand side here, and they're etched. And this is actually done in a clean room. And so how this device works is that here on the left-hand side, you see the voltage versus current plot of this device over a very specific current range. And there's some hysteresis. So as you ramp up the current, then suddenly you see suddenly the voltage will drop going down. And then as you ramp down the current, then the voltage will rise up again. And so what was discovered is that, well, first, if you apply a current bias, to sit at this point around 85 microamps or so, and then you flash light, a very short laser pulse. So in our case, it was about 180 milliseconds. Then you'll see the voltage will go down. And then when the light is turned off, then the voltage will sort of sit at this lower point of the hysteresis curve. And then afterwards, you turn off the current. So now you're not even applying a bias anymore. The light is off, current's off. And then you just let the device sit. And then later on, you can wait a minute, you can wait an hour, you can wait a day, and then you apply the current that you set in 1 again, this reading current. And then what would you find? So discover that even though after a minute or even an hour, actually happened for days, that even without any application of a current or light in between, when you apply the read current again, you see an oscillation possible. So there's an oscillating voltage that you can read out. And of course, if there was no light that had been shown on the device, then nothing will happen. It will just stay at point number 1 at the high voltage. So there will be no oscillation. So, and this is a very interesting discovery. No idea exactly why it happens. Actually, the existence of this suggests that there could be a new phase of matter in VO2 that hadn't been observed before. But it's really hard to kind of look into the physics of this state. But we were working on it. But nonetheless, we've observed this really interesting phenomenon, and we've studied this phenomenon from just from a heuristic standpoint, and so just very experimentally using these micro wires, but without probing into the material physics of this. And it's very interesting because this type of oscillation and this memory potentially can be used to, in fact, create new devices for computing in which the computation is done with oscillations. So it's a form of neuromorphic computing. So so that's all I have to say about the research that we do. It's a very broad range. It sounds a bit crazy, but if you can understand the bigger picture, that we're actually, in fact, very much inspired to work towards new technology for computing application, then I hope you can understand some logic here. And close, just want to thank all the students and postdocs and staff who and collaborators that we work with. Thank you.
So thank you very much, Professor Poon. I think that we are still, I want to remind everybody in the audience that we are collecting questions both on YouTube and via GatherTown if you message Kate, so canPOM on GatherTown. This session will go up until 1 p.m. and I don't want to take time from Tori and Fred. So I think what we will do is, if you have questions for Professor Poon, if we can get those in as well, and we can ask them after Tori's presentation. Would that be okay?
Yeah, that's fine.
Tori, are you here?
Yep.
Okay, so Tori will tell us now about backside integrated 3.5 on silicon lasers, and then following that, we'll have a quick Q&A. If you have any questions for Professor Poon, we'll combine that together. Go ahead, Tori.
Okay, am I up?
Yes.
Perfect. Well, thank you for the introduction. I'm a PhD student in Joyce's group at the University of Toronto, and today I'll be talking about the work we've been doing on backside integrated hybrid 3.5 on silicon lasers and modulators. And this work is an ongoing collaboration between our group in the University of Toronto and CEA Leti and Scintille Photonics in France. So just as a brief outline, I'll start by motivating the need for 3.5 on silicon lasers. Then I'll take a little bit of a detour and talk about indium phosphide on silicon modulators, kind of show how these come together in a new platform we're working on called backside on box or backside on buried oxide, and show how it's fabricated. And then I'll describe the DFB lasers and discrete mode lasers that we've demonstrated on the platform so far. So hybrid lasers, they've been gaining a lot of popularity lately for telecommunications applications. Before the introduction of 3.5 on silicon, or I mean, it's still even done today. If you want an optical transceiver with many channels in silicon photonics, you can handle polarization management and wavelength division multiplexing, like fiber to chip coupling, everything in silicon. But as Joyce mentioned, silicon doesn't produce light. So you need to co-package 3.5 lasers with the silicon photonics chip. To kind of alleviate these packaging difficulties and bring everything onto one substrate, the groups have been introducing 3.5 onto the silicon through a variety of bonding techniques. Shown here is a schematic from Intel and UCSB. They were the first group to show continuous wave electrically pumped 3.5 on silicon lasers back in 2006. They used an O2 plasma assisted bonding technique to bond 3.5 onto silicon. About a year later, CW lasers were demonstrated at IMEC, where they use a different approach, where they use a BCB as a bonding layer to stick 3.5 onto silicon. And then a few years after that, around 2010, Leti also demonstrated 3.5 on silicon lasers, where they use a thicker, maybe 100 nanometer or so, silicon dioxide layer as a bonding interface. And these bonding techniques can be done at the wafer scale by aligning like big arrays of 3.5 chips and then bonding them all into place on the silicon wafer at once. And it's a really convenient technique because you can use chips that are optimized for different wavelengths. So if you have like coarse wavelength division multiplexing and you need to span like 80 nanometers by putting different wavelengths of lasers on your chip, it makes it very easy to accomplish. But there are some issues with the process flows to develop these 3.5 on silicon platforms. One commonality you'll see in all of these three different platforms is the thickness of the silicon, which is at Leti, and the Intel UCSB platform is 500 nanometers. IMEC, it's usually thinner, but between 400 and 500 nanometers. And I'll show why we don't want that. And then another issue is that the processing is always done from the same direction, like from the top down. And so it makes it very difficult to integrate other materials. or even metal layers, like as Joyce showed in her slides on the silicon, a traditional SOI platform with multiple metal levels, it's very difficult to put that and the 3.5 both on top of the silicon. So typical 3.5 on silicon platforms are not very compatible with multi-layer platforms. So now, as a side note, kind of motivating, one of the reasons why we prefer thinner silicon is for capacitive modulators. So this was a project that we worked on with CEA Leyte a couple of years ago, where we made modulators that were formed. This was on a 300 nanometer silicon and 300 nanometers N-doped indium phosphide with a thin 20 nanometer oxide spacer. And when you bias this device, so this is the mode profile that's supported by the device. And when you apply a voltage bias, carriers accumulate on the interface. When carriers accumulate, they change the refractive index of the silicon and the 3.5 through the plasma dispersion effect. In indium phosphide, the effective mass of electrons is much lower than that in silicon. So you can get 5 to 10 times higher index changes in indium phosphide than you can in silicon. Here on the right is a cross-section of a device that was fabricated. And then we took these modulators I guess this is just a phase shifter, but we implemented it in Mach-Zehnder modulators to test the DC efficiency and the high-speed performance of these devices. And they showed a DC efficiency of about 1.3 volt centimeters, which is already twice as efficient as traditional like lateral PN junctions in silicon. An electro-optic bandwidth of 30 gigahertz, which is comparable to what you would get with a lateral PN junction in silicon. And shown here is open eye diagrams at up to 25 gigabit per second. The extinction ratio was pretty low, but this was limited by the low-speed photodiode we had at the time. But the efficiency limits of these devices are really set by the poor mode overlap between where the carriers accumulate right at the interface and the optical mode supported by the modulator, because the index of silicon is higher than 3.5. And yeah, the mode overlap is limited by material thickness constraints. So optimally, like if you wanted to optimize this geometry for the highest efficiency, you'd want a thinner indium phosphide slab. So in this case, it's 150 nanometers, and you'd want a thinner silicon slab to balance the mode. Shown here on this plot to the right is the confinement factor of just a 10 nanometer thick accumulation region in the silicon and in the indium phosphide using either 300 nanometer or 150 nanometer indium phosphide. So on the last set of modulators, we were using 300 nanometer indium phosphide, and the silicon slab was around 300. So we were operating off in this regime. Whereas if we had 150 nanometer indium phosphide with an optimized silicon slab, we'd be operating up in this regime. The overlap could be improved by a factor of at least 4. But that's not really doable on a front side platform because you can't make the silicon that thin or everything else won't work well. The way we solve this is through a process called backside 3.5 on silicon integration. This was developed at CEA Leyte with our collaborator, Dr. Sylvie Menezzo. And so this is a cross-section of what the platform looks like. You can see that here the silicon has been etched. Well, it looks like it's been etched upside down. It's been flipped upside down. And what used to be the box layer is now the interlayer spacer between the silicon and the 3.5. And then the 3.5 is bonded onto the backside. And this is a really useful platform because it's compatible with front-side multi-layer platforms. So this decouples whatever you had done on the top of the silicon previously with the back of the silicon where the 3.5 is being introduced. This box layer can be controlled extremely well. So we've seen plus minus 1 nanometer variation over a 300 millimeter wafer. And by using the N contact from the laser with the silicon rib, we have freedom to optimize the thicknesses to whatever we want to make the best modulators possible. And so here I'll just go through the process flow of how this is built. We start with just a standard SOI, but we choose our box thickness according to whatever we want the interlayer thickness to be in the finished devices. And then we pattern the silicon, clad it in SiO2 and polish it. We deposit amorphous silicon in certain areas, which I'll explain on the next slide, the motivation behind that. And we polish it again. Deposit more oxide, polish it again, and then it's flipped, bonded to a thermally oxidized silicon handle wafer, and the original substrate is removed with a combination of mechanical grinding and wet etching. The 3,5 is bonded and then processed, and now we have a 3,5 on silicon, or a 3,5 amplifier on the back of a silicon wafer. And these are just some images from fabrication. So on the left was 3,5 wafers that were bonded onto the original silicon wafer. These were just the first runs. This will become wafer scale, like die bonding eventually. On B is a fabricated laser. So this is the P contact, and then at the end contact wraps around the device. And in C is a cross section of one of the lasers on the platform. So you can see that the silicon here, the silicon rib, is upside down as compared to where the 3,5 is. So the first lasers we demonstrated were indium phosphide on silicon DFB lasers. So the amorphous silicon here was deposited on the silicon to improve the mode overlaps when you're trying to transition light out of this 3,5 on silicon laser and towards a grating coupler for characterization. And we formed a grating just by etching a grating into the 300 nanometer silicon rib waveguide down below. So this is a cross section here of what the laser looks like and the optical mode. And the grating was formed by etching this rib down to the slab level. And these devices worked quite well. They showed a threshold current of around 35 milliwatts and an on-chip power of about 20 milliwatts per side. So 196, 198, and 200 nanometer are just different grading periods that we tried. The lasers showed a side mode suppression ratio of about 50 dB, which is pretty good. And they operated up to about 80 degrees Celsius, which was limited by the thermal resistance of the SiO2 below the laser, which is very thermally insulating. And then the next set of devices that we have worked on this platform so far are called discrete mode lasers. These were developed at Tyndall National Institute back in about 2006, and they've since been commercialized by Ebrahim Photonics, although they're not a very well-known type of laser design. And the way they work is that they're based on a traditional Fabry-Perot laser cavity design. So you start with a traditional Fabry-Perot laser, just an amplifier with two broadband mirrors. And what they did at Tyndall National Institute was they computed from perturbation theory, what is the impact if you had put some small refractive index defect or refractive index perturbation in the laser cavity, as you can see in this schematic of a lengthwise, like a diagram of a Fabry-Perot laser diode. Here they had introduced 25 weak refractive index perturbations. They calculated what effect those perturbations will have on the threshold gain spectrum of the laser and came up with a method called the perturbative inverse scattering algorithm for aligning these perturbations in such a way, or the effect of these perturbations in such a way that you can tailor their effect on the threshold gain spectrum such that one mode in the spectrum will have a much lower gain threshold than all other modes. So in this case, just by etching 25 weak refractive index perturbations into their laser cavity, they were able to make this broadband, Fabry-Perot laser, become single mode. So we did this by now, rather than using the amorphous silicon here to extract light from the laser diodes, it's now to efficiently transition between an amplifier and broadband DBR mirrors. So we have a rear mirror that's high reflectivity and a couple lower reflectivity front mirror designs. We define a threshold modulation function that we want. In this case, it's a sinc function modulated by a Gaussian, where just one mode within a broad spectrum, so the width of the DBR mirrors, has lower gain than all the other modes. And we use a perturbative inverse scattering algorithm to define a feature density function that we sample with either 25 or 50 slots that we etch into the silicon rib to reduce the gain threshold of just one mode. And shown here in E and F are the computed gain threshold spectrum for 25 slots. And you can see one mode has about 10% reduced gain threshold than the other modes, or with 50 slots rather, it's about 20% reduced gain threshold. And then these are the characteristics of a fabricated device. So FPL and FPH are Fabry-Perot lasers with low or high reflectivity. And then DM, L25, or H25 is the same lasers, but now with 25 weak refractive index perturbations in the cavity, and 50 as with 50 weak refractive index perturbations in the cavity. And so the output power decreases a little due to additional scattering losses in the laser cavity, but the impact that it has on the spectrum of the devices is really interesting. So just below threshold at 30 milliamps. Here in blue is the Fabry-Perot laser, like many modes being amplified and near threshold. In the discrete mode laser spectra, the modes have been highly suppressed. Just above threshold, you can see in the discrete mode lasers, a single laser line is starting to dominate. And then well above threshold, the Fabry-Perot lasers are of a broadband spectrum with many laser lines, whereas in the discrete mode lasers, they're single mode and they operate with a side mode suppression ratio over 60 dB. And then we also measured their line widths with a delayed self-heterodyne interferometer. Oh, so these are some RF spectra from the interferometer at 80, 120, and 160 milliamps of bias to the laser. And we fit this with a Voigt function to extract the Gaussian line width, which is pretty much constant. This probably comes from the interferometer, which had about 25 kilometers of fiber in it, so it's quite subject to noise. But the Lorentzian line widths from fitting, they follow the expected 1 over p linear 1 over p relationship, and show line widths that are below 20 kilohertz. So if you come from a solid state laser or a fiber laser background, this might not sound very impressive. But for semiconductor lasers, this is 1 to 2 orders of magnitude better than what you would see in traditional monolithic 3.5. So in summary, we've demonstrated so far indium phosphide on silicon Mach-Zehnder modulators with VPL of about 1.3 volts centimeter and a 3 dB frequency of around 30 gigahertz. We introduced the backside on box platform, demonstrated O-band 3.5 on silicon DFB lasers, O-band 3.5 on silicon discrete mode lasers. And in the future, our next projects are going to be on developing the backside on box modulators and backside on box photonic integrated circuits, such as transceivers that combine all these components together. So I would just like to thank the many people not listed on papers here, but that worked in the fab at Leti, helping us to build these devices. And thank you everyone for your attention.
Thank you very much, Tori. So just a reminder to everybody, if you have any questions, please put them into either via YouTube if you're watching us through there, or message them to canPOM if you're in Gathertown. And because there's a slight delay between YouTube and between our actual call here, the questions for Professor Joyce have just come in. So if Professor Joyce is still here, we have time, I think, for 2 questions. So from Connor Mascara, question for Professor Poon. What is the dominant loss mechanism in your visible wavelength waveguides?
Yeah, the dominant loss is scattering. There's also a bit of absorption at the blue as you go to shorter wavelengths in the blue. So, but it's scattering is still the dominant source. And then I see the other questions for the VO2. I'm on the YouTube, right? The
Yes,
second
sure.
question
maybe,
is
you'll read it.
the phase change. Yeah, sure. Yeah, about the VO2 phase change. That we don't know the origin of this. To be more specific, the phase change origin, there are theories around it, so that's known. But the non-volatile memory aspect, like the fact that after we optically sort of addressed this device, and then an hour later, you can read out the device as oscillations. That aspect, we don't know. We don't know why yet. Then the next question is, do you think this effect is specific to vanadium dioxide, or could it be something else? Could be other phase change materials. I think that this particular phenomenon that we observe might be only in vanadium dioxide. It may be due to the existence of a specific state of matter, actually, a state of matter in that first kind of transition that hadn't been observed before. So I don't know if other materials would have that.
Okay, thank you very much. So I think our session ends at 1, so I want to make sure that we don't...
Fred hasn't given his talk yet. So.
Yes, so I think that it might be good for Fred to go ahead, and we'll have a combined... Any questions you have for Tori and for Fred, please put them in. And Fred, if you can go ahead. Thank you so much.
Hello. Yeah. Okay. Okay. So hi everyone. So today I would like to kind of give a talk on our group's endeavor of using integrated photonics for neuroscience application. So kind of before I start, I would like to kind of say like, yeah, this project is actually an effort for like multi-institutional kind of an effort put into this work. So I will not solely just like take credit for all of the results I will show later. It's done by quite a lot of people that's involved in this project. So before I kind of go into the project, I would like to kind of give you kind of a bit of a background on like what are the kind of like the application of photonics in neuroscience, and then what kind of motivates us to use integrated photonics in neuroscience application. So one of like kind of like an interesting application you can use photonics in neuroscience is these optogenetic stimulation. It is essentially a technology that you use gene editing technology to modify certain neuron such that they have a light sensitive ion channel. So when you shine light onto these neurons, they will these ion channel will open up, and then essentially the neuron activity will be triggered and then send a spike to the next neurons, and essentially it's doing stimulation. And then kind of the advantage of this optogenetic stimulation compared to a conventional electrical stimulation is that since it's using a gene editing technology, you can actually tag these light sensitive ion on specific cell type. So either an excitatory neuron or an inhibitory neuron. So now you can do some you can excite the neurons or inhibit the neuron, which is hard to do in the electrical stimulation regime. And then the second application that photonics is useful in neuroscience application is calcium imaging for functional imaging. And the idea of calcium imaging is that people tag these fluorescent protein on calcium ion. And then these calcium ion are actually an indicative of whether the neuron is activated or not. And so by looking at the concentration of these fluorescent protein using a fluorescent microscope, you can actually see whether the neuron is activated. So the spike you see here are when the neuron's activated. And then the good part about this technology is that you can get a kind of a cellular resolution of where the activity is happening. And this is like really great for understand the brain circuits in great details. However, kind of the two kind of application I mentioned about, most of the application are still using bulk optics. So actually, you actually limits like the animal behavior and as well as this kind of the experiments you can do. And our group wanted to leverage integrated photonics to kind of make these systems a bit more compact, and also as I'll kind of briefly talk about later, it also provides some new advantages compared to a conventional bulk optics technique. So the idea is using a silicon nitride layer as waveguide to guide lights down to the tip of the probe, so you can shine lights into the samples to either do stimulation or maybe doing some functional imaging, as I will show later. And then the good thing about using integrated photonics is that you can integrate these micron scale devices such as grating coupler, which is being used here as like a kind of an emitter to emit out the light to the samples, as power splitter, optical switches, etc. And then another good thing about this integrated photonics is that these devices, the chips are actually quite compact, so it can be implanted into the brain to overcome the light scattering limitation inside the brain. So you can actually do some experiments inside the deep brain regions that conventional bulk optics cannot do. And as kind of Joyce mentioned, we also actively work with the foundry, so then we can make these probe massively manufactured, so then we can disseminate this technology. And then from one wafer, we can get about 1,600 probes, which is quite a lot. And then we can also shape like we can have different various shape of the probe, such as like these 4-shank probe and the single shank probe for different animal experiments. And then these wafer again is done by our collaborators, fabricated by our collaborator AMF. So just to kind of give you like a brief overview of kind of like the system setup. So one thing to mention is that these probes are actually all passive. So there's no electronics components on the device to generate heat. As heat generation is actually quite a concern in animal experiments. And the way we kind of deliver light to the probe and then into the tissue is by using a scanning system shown here. And the idea is that we will have laser light shooting out and then toward this MEMS mirror shown here. And then this MEMS mirror will direct the light to a different fiber core on the fiber bundle. And this is the image here will be showing kind of the facet of the fiber core as we kind of change this the MEMS mirror. And then this enable us to do emitting pixel switching on the probe, as demonstrated here. So we can actually do any kind of patterns with this kind of scanning mechanism on our system. So so the first kind of application I would like to talk about is this beam steering neural photonics probe. And then the idea is that we use optical phase array to achieve beam steering inside on the probe. And then the idea is kind of by setting kind of a delay lens on the emitter. So these circles represent a grating coupler or like emitters on the probe. And by setting a proper delay lens for the emitters, we can actually tune the wavelengths. Oops. Yeah, we can actually tune the wavelengths. Yeah, I think there's some problem with the animation, but essentially, as you can kind of see in this equation, when you change the wavelengths, you can actually change the angle that it is steering. And then these devices are actually quite compact, so we can put them onto like the tip of the shank, so then they can be implemented for very targeted kind of optogenetic stimulation. And here are some of the kind of validation we have done inside a brain slice. So kind of the setup is shown here, where we insert the brain probe into the brain slice, and then on the top we have a fluorescent microscope to examine like the light within the brain slice. And at the bottom, we have a micro electro array to record the electrical activity happening within the brain slice. And as shown in this video, we're actually able to achieve a beam steering in the kind of a forward scattering medium, like a brain slice. And then the light you see here are actually fluorescent light from the tissue. And this kind of ensures us that the light is indeed inside the tissue. And then that's how we can kind of observe. And then the fact that we can observe these beam kind of steering around shows that the beam steering is achievable in the brain slice. And then kind of the steering range that we can obtain is about 40 to 50 micrometer, 100 micrometer away from the probe. And then the wavelength tuning range is about 6 nanometer wavelengths. And then as you can see at the bottom here, the full width half max of this beam inside the tissue is about 12 micron, which is roughly around the size of a neuron. So again, this kind of shows that we can do a very targeted stimulation within the brain. So on the kind of the electrical activity side, we wanted to check whether the probe can deliver a sufficient power to the brain slice so we can trigger a neural activity. And as demonstrated in the center of the image, by turning the laser on and off, we can actually see quite an obvious spike occurring, being modulated by the light that we send down. And in addition to that, we've shown that by using different pixels on the probe, which is pixel 1, 2, 3, emitting pixel 4 on the shank, we can actually kind of vary the spike rate on 2 different electro on the MEOA, so channel 53 and channel 51. And by going from pixel 1 to pixel 4, we can actually change the spike rate ratio of these 2 channels. And then the data points with the same color indicates different power. So in fact, you can see here that no matter how you change the power, you cannot replicate what's happening on all of these. You cannot replicate using one of the pixels to replicate the other. And this shows that this indeed can have quite an interesting application for doing kind of a pattern stimulation inside the brain of a mouse. So the second application I would like to kind of talk about is using probe for light sheet fluorescent microscopy. And then the idea of light sheet fluorescent microscopy is that it sends in a sheet of light, and then the imaging system that you have focus on that sheet of light. So then this kind of enables very low background noise from the sample compared to conventional epifluorescent, which is essentially illuminate the entire sample size. And then this actually enables an imaging system of a very large volumetric imaging. As kind of shown here, you can get like very good image from here. Just to kind of keep in mind, they also done some clearing, so essentially kind of removing all the scattering medium inside the tissue. So that's why they actually get like a very crisp image. But then again, if inside like a normal inside normal tissue imaging, light sheet fluorescent imaging is expected to be to produce better image quality than epifluorescent. However, kind of the downside of the system is that it's currently being is implemented in using a bulk optics. And then, so it actually really limits kind of the movement of the animal that you wanted to image. And so the thing we wanted to kind of improve on is how can we make this light sheet fluorescent microscopy head mounted and miniaturized, so the mouse can move freely, and then you can still do imaging with a higher image quality. And the idea is to use multiple gradients on the shank to synthesize a light sheet as demonstrated here. So we actually illuminate these gradient coupler at the same time, and then when the beam comes out of these gradient coupler, it forms a uniform sheet of light. And this kind of mechanism is like the way we route it is using this kind of routing network. And then here's an image of like us. We actually have like 5 different light sheet pixels on the shank. So on the shank, so we can actually adjust the light sheet coming out, like which plane should the light sheet come out, and then this allows us to obtain a volumetric image if we have a electrical tunable system, imaging system as shown here. And then kind of the idea is that we wanted to use this probe and then integrate it to maybe some sort of like a more commercially available epifluorescent head-mounted microscope shown here. And then this could allow us to make a head-mounted implantable light sheet fluorescent microscopy that's able to produce a much higher image quality results than conventional epifluorescent imaging. And here's some kind of validation we've done. So in our validation, we didn't have inserted like the head-mounted microscope as demonstrated in the previous slide. We just use a conventional epifluorescent microscope as a benchmark, just to see if we use a light sheet illumination versus epifluorescent illumination, which one would provide a better image contrast. And as demonstrated here, and this image, we're actually imaging mouse with transgenic fluorescent protein that contains GCAM6S. And then the part that we're imaging is dentate gyrus, which is a part of a hippocampus. And then you can see here that for epifluorescent, you get this very bright background. Just a sec. Oh yeah, you get this bright background noise. However, in this light sheet imaging system, we get a very crisp like contour of the neurons. And then on average, we actually get about 3 to 4 times of the contrast enhancement for the neurons compared to epifluorescent imaging. So another thing we wanted to check is whether the light sheet probe can provide sufficient intensity so we can see calcium calcium dynamics of the neuron. And then that's kind of demonstrated here. The probe can in fact provide sufficient power for doing calcium imaging. And then we have also tried to plot it out the kind of a calcium concentration change of the neurons that's flashing. And then it shows some good spikes going on within the samples using the light sheet probe. So kind of in summary, I have kind of showed 2 examples of how our group uses integrated photonics to create new tool sets for the neuroscience community. First one is using this beam steering mechanism for targeted optogenetic stimulation. And second is that we wanted to create this light sheet probe that enables a head-mounted light sheet microscopy on an animal. And currently our group is trying to develop a multimodality probe, so including the optics, but also adding on top of that with some electro and microfluidics, so we can gather more information from the brain. So then more experiment, there's more flexibility for the experiments. And we're also actively working with the foundry to produce these probes and then trying to get the fabrication yield higher. And last, our kind of ultimate goal for this project is that we wanted to implant these probe and then allows freely moving animal experiments with these neural photonics probe. And then there are definitely some challenges there that we were trying to face, trying to resolve, which is trying to make the device a bit more user-friendly, so common neuroscientists scientists can actually use the system, such as they are able to plug in and unplug the fiber, so it's easier for their experiments to conduct. And then also trying to have a better, robust packaging process, so we have more probes to be made. And at last, we wanted to have a robust housing, so and also a compact housing, so the probe can be head mounted for animal experiments. And hopefully, if we're able to achieve all of these, we can help the neuroscientists to create new experiments that can hopefully work towards unravel kind of the mystery inside a brain circuit. And that kind of concludes my presentation. And I would like to kind of give a special kind of credits for Wesley Satcher. He's our group leader within the group. And then he's the person who definitely kind of initiate like the design of the probes and then and try to bring the probes to the current states. And I would like to also thank all the other people who have worked on this project, as well as our collaborators from different institutes. And thanks you for your attention.
Thank you very much, Fred. The beam steering results are really amazing. Unfortunately, we are out of time. If you had asked a question for this session, it will be answered inside of a YouTube chat. And our speakers are going to be there and answering. And we're going to go right to the next session because we're a little bit behind time. Next up, we have Professor Ziliang Yi from UBC to introduce our next research showcase.
Hello, everyone. Our next speaker will be Professor Ebrahim Karimi. He is an associate professor of physics in University of Ottawa. And yeah, you can see, hello, Karimi. You can see his Star Wars background already.
Oh, yeah.
Professor Karimi got a PhD in Italy, University Napoli, and he currently holds a Canada Research Chair in the field of structural light and is a group leader of structural quantum optics at the University of Ottawa. He has also a adjunct professor in ISBS Iran, a visiting professor at the Max Planck Society in Erlangen, and is also associate editor of Optics Express and New Journal of Physics. He has won many awards. He has won Ontario Early Research Award, Young Research Award in Faculty of Science of Ottawa, and multiple in the Optical Society. And I think just this year he was elected a member of a College of New Scholars, Artists and Scientists of Royal Society of Canada. So with this introduction, Ebrahim, I would love to give you the floor, and the whole show and tell for each group should last about 45 minutes, and I will encourage the audience to ask questions, let's say during the talk in the Gather Town or YouTube. We will try to reflect it and pose to the speaker as fast as we can. Yeah, please.
So thank you very much, Ziliang. And of course, Orad and Kate, which, and of course, there are many other people behind of these activities. So thank you very much, guys, for doing this. I think you started much earlier than pandemic, going for online meeting idea, which is amazing. And nowadays, everyone in the world is fighting for having online meetings. So thank you very much for doing this, and also for inviting me and my team. So as you say kindly, so I'm mainly based at the University of Ottawa, so I'm officially hired at the University of Ottawa. I'm associated with different centers, so is Max Planck Institute in Erlangen for the Science of Light, and Center for Photonic Research at the University of Ottawa, and recently launched Center for Extreme Photonics at National Research Council of Canada, and also adjunct professor at the ISBS, which is a Advanced Institute for Basic Sciences in Iran. So the research activity that we are doing is structured quantum optics, and I will give an introductory about less than 4 minutes, just to tell what we are doing, and then I will pass it to senior members of my team, which they will go in deep and they will explain some of the funds that they had during past 5 years. So like many physicists, I like, and many optics people as well, quantum optics people, I like to start with elementary particles. It's very strange. So high energy physicists, they have this table, but we use it. So my research activities are mainly devoted to 2 particles in this table. One of them is a photon, of course, which is an elementary particle for electromagnetic interaction. It has no mass, it has no charge, and interestingly, it has a spin of 1, but only 2 values is permitted, okay, due to the fact that it doesn't have a rest mass. And also, we do activities with electron beams, free electron beams in transmission electron microscope. On the other side, what we have is electron has a rest mass and also has a charge, which makes it more interesting for other activities that we do with structured electrons. So if I want to briefly introduce to you what I mean by structured quantum waves, that you have many different degrees of freedom. So since your audience, there are optics people, I will just concentrate on photons. So when we talk about photons, photon can have a specific transverse mode, can have a specific polarization, can have a specific wavelength. So assuming that we are making a photon which is a coherent or incoherent superposition of all of these different degrees of freedom together. So you take all of these different degrees of freedom, you make a specific superposition of them, either you make them incoherent or coherent, and then what you end up with, we call it structured quantum waves. This can be done with photons, can be done with neutrons, can be done with electrons, or can be done with any particle that you want, or many body system. For example, I have a joke that I say that even my body is a quantum, it's just a matter of money. So if you cool me down, then you will see my quantum feature. If you make this coherent superposition of different degrees of freedom of many bodies that I have, many body problem that I have it here, then you can end up with structured quantum waves. For example, the image that you would see in the left side is a single photon, can be a single photon or a coherent beam, which is a superposition of different radial modes, different orbital momentum modes and polarization. And then what you end up with is a very complex intensity and polarization topology. So we call these structured quantum waves. We have different techniques in laboratory to create them. One of them, it can start from bulk optics. You design really optics elements, which can be, let's say, about 20 centimeters size, which you can structure these objects, or you can go to plasmonic structure, which you can have about, let's say, 80 nanometer thickness that can shape the optical beam, or you can have a liquid crystal technology, which I think Flex is talking about that soon. So why they are important? For example, they can give you many interesting fundamental problems that you can solve. For example, in 2015, in collaboration with my colleagues in Germany, Peter Benzer, Gerd Leutz, and other colleagues there, we created the first 3-dimensional topologies, which was a puzzle for the community in the shape of Mobius strip. So polarization forms a Mobius in free space. And then recently, 2018 and 2020, we created nodes, polarization nodes with structured light. those beams, they provide many different aspects. For example, they can be used for enhancing a microscopy, which is a slit microscopy, and you can enhance the resolution by 20 times. So this the reason this one of the application of the structured light, which Stefan Hell got a Nobel Prize in chemistry for it. However, if you look at the photonics side, I don't want to talk about the electron side at this community. If you look at the photonics side, this provides you many different alphabets. So the alphabet that you can use it can be increased and can be essentially unbounded. So this provides you to have access to high dimensional Hilbert space for doing quantum computations or doing quantum communications. So in this case, for this specific slide, my team, and at that time Alicia was a bachelor student, they performed a QKD between two different buildings at the University of Ottawa, and was one of the earlier free space high dimensional QKD in the world. So if I want to tell in one slide what we are going to do is, the goal of my team is building up an extreme quantum microscope, which you can get fast motion and high resolution in atomic scale resolution, and even going to attosecond temporal resolution. We are aiming, and we are a member of a big community, which is Quantum Internet Canada. So we are trying to help and understand and perform QKD or quantum communications and building up a network around, in Canada. And on the other side, we always want to have a fun and answering fundamental questions. I mean, building up new devices and understanding what's going on with the fundamental physics. So, of course, this is not one person activity, is the group activity. So many other people in the team. Alicia and Felix, as just two senior members of the team, they will give an overview of these activities. And of course, I have to thank my collaborators all around the world, from Max Planck to NRC, which they helped us with performing this sort of experiment. And without the funding agencies, always is impossible to perform this sort of activity. So I will pass it to my students. I think Felix will be the first, and then Alicia. And if you're interested to join the group, always there are possibilities to do collaborations or joining as postdoc, PhD, or master student. You're always welcome. So just send an email along. Thank you.
Hello. All right, so thank you very much, Ebrahim. My name is Felix Hufnagel. I'm going to be talking about some more of the specifics of our generation techniques that we use to generate these structured modes of light, and then also just give an overview of kind of the breadth of experiments and of interesting research topics that we can cover with this. So is my screen showing properly there? Yep, awesome. Okay. So we're talking about structured light, and what we're going to be focusing on here today and in our lab in general is the polarization and the spatial modes of light. And so you could, of course, expand to include stuff like the frequency of light and other degrees of freedom. But these two separate degrees of freedom are what we're going to be focusing on today. And so we have first our spin angular momentum, which is maybe the most common type of degree of freedom of photons used in our optics labs as polarization. So we have left circular and right circular polarization, and these give you an angular momentum component to your photons. And so this is pretty common. We know how this works. What might be less familiar to everyone here is the orbital angular momentum, as Ebrahim mentioned. And so here, as opposed to changing the phase around the axis of propagation, we have this kind of azimuthal dependence on the phase here, sorry, as opposed to the polarization. So here, your OAM of L equals 0 would just be your typical Gaussian mode that we're all used to using coming out of our laser sources. And then if you had a full turn of the phase around from 0 to pi around the axis of propagation, this would be an OAM of 1 and an OAM of 2. And what's interesting about this is that we get an unbounded Hilbert space when we're talking about quantum systems. So as opposed to just having your left polarization and right polarization as you have in the spin case, here we can go to theoretically infinite magnitudes of OAM. And so when we think about generating these types of modes, we of course know our quarter wave plates for generating these circular polarization states or the spin states. And then for orbital angular momentum, the most trivial way to think about it would be a spiral phase plate. So here you just have a piece of glass that has a cut, which will represent your kind of 0 to 2 pi phase distribution. And so you just have this cut and this distance d separating the cut such that you produce your helical beam of OAM equal to 1 or OAM equal to 2. And so this is really cool, but this is quite bulky. And so we want to be able to think of ways that we can generate some beams without having to use these bulky spiral phase plates. And so this is where liquid crystal technology is going to come into play. And so this liquid crystal substance has birefringent tendencies, and you can often tune this birefringence by applying a voltage to this OAM. And so let's think about, we have some plate that's containing our liquid crystal cells behind it, and we want to orient these liquid crystal cells in a certain direction so that we can get precise control of the birefringence at different planes. So what we're going to do is we're going to shine some incident linearly polarized light onto this cell. And so here we have different incident polarizations. And when we do this for long enough, then we get the alignment of all of these liquid crystal cells in each of these respective planes. And so then what we have here is what you could see as being 4 different pixels where the birefringence is dependent on the way that we oriented these liquid crystal cells. And so the most general way we want to do this is for making what we call Q plates. And this is what we're going to use to generate OAM states. So here we're going to have a azimuthal symmetry about the way that which we're aligning the liquid crystal cells. And so we want this azimuthal symmetry in a way that when we send in our left and right circularly polarized light, we get out the opposite polarization with now this added e to the I phi phase, where this e to the I phi term is where we're containing our OAM. And so if we have this Q plate with our value of L equals to 1, then we could send in left circularly polarized light and we get out L equals to -1, or we send in the other circular polarization and we get L equals to -2. And then as you think about sending in a combination of these circular components, you can get what is seen here in these green slides as a polarization dependence in the azimuthal plane. So these we would call structured vector vortex modes. And so that was to generate a general Q plate. But with our setup, what we have is we have this digital micromirror device which is just a screen with a few hundred pixels. And so we can actually generate any arbitrary kind of pattern that we would like and imprint this onto our Q plate. So as opposed to doing an azimuthal symmetry, we might have some strange pattern like this. And in this way, we're able to produce these very interesting spatially structured beams that we see here and here. And we could generate a Q plate that creates an OAM beam of, here we have L equal to 200. So we can create these really interesting modes of light. And then we can bring these into our lab and see what we can do with these. And so again, just demonstrating kind of the way that we're able to arbitrarily generate these interesting states of light. We have here what we call a Laplacian magic window. And so there is an interesting theory paper by Michael Berry a few years ago describing how we could generate these interesting magic windows where upon propagation of light through this magic window, you have very fine phase variations at this plane of the window, such that you can still look through the window, but then upon propagation of coherent light through this window, you get kind of this interesting intensity pattern at the plane upon propagation. And so this is just because you can take some kind of interesting image like this and compute the desired phase that you would want by the Laplacian of this intensity, and then allowing the propagation of light through that phase, you get the production of these interesting intensity patterns at an arbitrary plane of propagation. And so now going back to those Q plates where we're sending in these non-circular polarizations and creating these kind of interesting polarization topologies, we have what you could call completely circular points in the polarization topology. And so this is essentially a singularity in the polarization where we have a perfectly circular polarization. And so we don't have any component of the S1 and S2 Stokes parameter. And then in the same way, you could have a linearly polarized light where here you don't have any component in the direction of the circular polarization. So in this way, we are able to create some polarization singularities in these optical beams that we produce. And so here we can just see if we create one of these interesting polarization states, you have this circular C point polarization singularity here, and you have a line of these linear polarization singularities surrounding that C point. And so we can create any kind of arbitrary different types of these interesting polarization structures. And then what we can think about is allowing some of these polarization structures to propagate through space. And upon propagation, what you can get is that when we follow these polarization singularities, they draw out these lines in the Z propagation direction. And these lines can actually form knots. And so this is just a really interesting demonstration of how we can see these mathematical objects that we have in knots being presented in the optics lab through the propagation of these interesting structured beams. And so furthermore, you can get, instead of just the propagation of these singularity lines, you could get a propagation of these surfaces, creating these really exciting polarization topologies propagating through space. And of course, this is just an interesting phenomena to observe in itself, but we can also consider actually sending information by transmitting these optical polarization knots. And so you could think about ways in which you encode the factors of a prime number into the twists of a polarization knot, and you could send this from an Alice to Bob to have some secure communication. So now we're going to move kind of from the optics side of these structured beams towards the more quantum side of our lab. And so the first thing we're going to look at is interaction-free ghost imaging. So we have this cool phenomenon of interaction-free imaging, where if we have just our general interferometer, we should always get some output at a certain port here. And then even when we move to the quantum case, we still get all of the output at one port of the interferometer, independently of whether the single photon traveled through the left path or the right path. Now, if we go ahead and interrupt this interference in some way by placing, say, an object that we want to measure in one of the arms of the interferometer, what we get is a destruction of this interference. And so here, what you're going to get is we're going to get some intensity coming out of each arm of the interferometer. And then as we move to the quantum case, you can see that even if we just send a single photon that doesn't interact at all with this object in the left arm of the interferometer, we still get some measurement here in the opposite output port. And so this is the idea of interaction-free imaging, and extending this with multiple interferometers in the Zeno effect, you could get it such that 99% of the time you're getting your measurement out of the arm that doesn't have the object in it. And so then you can think about these kind of techniques for measuring an object without actually sending a single photon of light to interact with that object. And so this has been shown in the past, but a cool idea is to introduce to the interaction-free imaging this idea of ghost imaging. And so ghost imaging is another quantum effect that we use, whereas as opposed to just measuring whether there's some object there or not, we could put some object on one side of an entangled photon and then have a bucket detector behind that object. And then in the other arm where we have its entangled pair, we could have a camera. And so this photon that's going into the camera will not ever interact with the object that we're trying to measure, but yet what you'll still get is the appearance of the object in the camera if you post-select on to coincidence measurements with the bucket detector. And so by combining these two things, we're able to get this kind of interaction ghost-free imaging setup in which the photon that we measure both doesn't interact with the object at all, and in fact, the other photon, which is going to the bucket detector, also doesn't even go past this object. And so to extend this just a little bit by using our structured light, we're going to consider using our OAM degree of freedom. And so we have, of course, our general Rayleigh resolution criterion, where as two point sources come closer and closer together, there's a point at which we can't differentiate them all at all. However, as we go into the quantum world and look at the Fisher information that we can have between these 2 point sources that are getting increasingly close together, we can actually find that we have a lot of information about these two sources in the derivative of the point spread function. And so by considering this, what we could want to do is, as opposed to just measuring these two intensity sources, so as say two Gaussians, we maybe want to make a measurement on the first LG mode, the first Laguerre-Gauss mode. And so in this way, in our experimental setup here, you introduce an SLM. And so then we project onto the LG11 state. So this would be a two-lobe state. And we can actually get more information about these 2 point sources than we would if we were just projecting onto the Gaussian mode. And so then extending this again to the ghost imaging experiment described above, we can get some really interesting ghost imaging results where we're increasing to these super resolution limits. So another thing we can do is consider compressed sensing of these kind of OAM type states. And so we consider a quantum state that has low rank. So here we have a low rank equal to 2 state. And so you can see that really to make a measurement of this state, there's only 2 kind of interesting features of the density matrix. But to make a full characterization of this density matrix, we would have to take this like 10 by 10, 100 different measurements. And so we've come up with this interesting protocol where by assuming a low rank state, you can gain some information about the density matrix while only taking 2 or 3 measurements. And so we do this by taking information on the of the GUI phase of these OAM states. And we can do this by changing the Z plane of a camera and making measurements just on the intensity of these states. And here we just have some simulation results showing that even in L equals to 7 states, so this would be a Hilbert space with 15, with dimension 15, you can still get nearly perfect results in even up to rank 4 by just taking 2 intensity measurements. And so this is a really big increase on the ability compared to taking, you know, an L equals to 15 squared measurements. And I'm gonna just go pretty quickly through the end here to make sure Alicia gets enough time. So finally here we can just, we can think about what kind of correlations we can get out of an SPDC measurement. And so anyone working in quantum photonics, you know that you can generate some entangled photon pairs out of SPDC in something like a BBO crystal. And it's been shown before that you can get correlations in the OAM through this SPDC process. But you can even go a step further and actually realize correlations in the P mode. So this would be what you see here. This is a regular Gaussian. This would be a Gaussian with a P equals to 1. So you have this first radial mode here. And so pumping with these radial modes, we can get some correlations in the radial modes as well. So this gives an opportunity for high dimensional degrees of entanglement coming from SPDC. And I will just go quickly through there. Thank you very much. And I'll now invite Alicia to talk about some of the quantum communication aspects of the work we do.
All right, so thank you, Felix. I can just, if you stop sharing, I can start sharing.
Yeah. There you go.
Okay, cool. Bring up the laser pointer. All right, so hello everyone. And so thank you to Ebrahim and Felix for doing the heavy lifting of explaining kind of the fundamental basics of what our group does. And so today I'm going to give you a showcase of one of the quantum applications that we can use structured photons for, and that's namely quantum cryptography. In particular, we'll take a look at 2 of our proof of concept experiments that we've done in the past couple of years, where we realized quantum cryptography in so-called realistic environments. So outside of the lab, we have, like you can see here, no vibration isolation and no humidity or temperature control. So this talk is kind of partitioned into 3 parts. We're going to review kind of the basics of quantum cryptography, why we care about it, and then move on to the free space and underwater experiments that we've done. Okay, so let's recall of why we care about quantum cryptography, starting with the age-old problem of Alice and Bob want to securely exchange a message. In the real world, this could be, say, you want to access your banking information or something like that. And we can, and Alice and Bob can use a our kind of current encryption schemes, such as RSA, which are based on mathematical difficult problems, such as factoring prime numbers, but that are computationally expensive to break. So in this way, they can kind of generate a key, which they can encrypt their message, and they're good to go. Now, where this becomes a problem is where we start to introduce quantum computers, which for a lot of fields is a very new and exciting thing. But when dealing with information security, it's not so good, because it's actually been shown that quantum computers can break our current RSA encryption schemes using something called Shor's algorithm. So a problem, to be sure. And while our current quantum computers are still a long ways from breaking RSA, it's important to develop our strategies now so that our information will be secure well into the future. So far, we kind of have two strategies to go about doing this, something we call post-quantum cryptography and quantum cryptography. I'm not going to talk about post-quantum cryptography, but to get a sense, it's novel classical encoding schemes that use algorithms that haven't been shown that quantum computers can break yet. So that brings us to, okay, what about using quantum cryptography, where now we're actually relying on kind of these fundamental principles of nature and quantum mechanics that actually makes our schemes conditionally secure. So you can think about the superposition principle, the Heisenberg uncertainty principle, we have the cloning theorem, and using entangled states. And so one of the quantum cryptographic tasks that we'll be concentrating on is something called quantum key distribution. And so this is protocols in which it's distributing, just like the name says, distributing the key between Alice and Bob, leveraging quantum states. So this isn't transmitting the message, but it's generating the key that they can use to encrypt. So QKD makes use of three elements that I like to think about. So we have the degree of freedom. This could be polarization, this could be time bin. In our case, we're going to be looking at structured photons, which we've heard so much about. We also need a QKD protocol. So this is actually ways in which we generate some states, we measure some states, and we can kind of recover a key from there. I will briefly talk about kind of the cornerstone and the first protocol that was introduced, which is BB84, so by Bennett and Broussard in 1984. But there's a whole slew of other ones that have come out since then that you could go look into the literature. And finally, it's also important that we have a quantum channel through which we can actually transmit our information. And this could be, so we're all familiar with our kind of fiber networks that go across the world. But in the quantum regime, since we cannot amplify our signal, we can only get so far. So we actually need to eventually start thinking about free space channels to ground stations to satellites, and et cetera. And we'll also kind of start looking into preliminary results of what it would mean if we were to transmit these sorts of protocols in an underwater environment. Okay, so speed run of explaining BB84. So the key factor here is that it's based on what we call mutually unbiased bases. So we have two sets of bases, which if you were to generate a mode in one basis, but then make a measurement in the second basis, we actually gain no information. So it's an equal probability that we'd actually get a 0 or a 1. So how BB84 goes is Alice will generate a random string of bits. So these are just classical 0s and 1s. And she'll then choose a random mob to which she can generate a quantum state. She can send these states one at a time to Bob over her quantum channel. And Bob can then randomly choose a measurement basis, measure a certain state, and then record the corresponding classical bit. So how they retrieve the key from this, so as of right now, they haven't actually communicated anything, but now they can call each other up on, say, just a classical phone line and tell each other which mub did Alice prepare in and which mub did Bob measure in. From this way, they can sift through their photons and only keep the ones where it was the same. So you can see here on Alice's first and third and Bob's first and third, they actually picked the same mub. So from there, we get what's a raw sifted key. So I'm just going to throw this up. This is kind of a theoretical, what I call probability of detection matrix. for what happens when Alice generates a certain mode and Bob measures on a certain mode. So you'll see this kind of popping up a lot in the next couple of slides. Of course, in theory, we would get a perfect key with no errors, but there's always maybe an eavesdropper that we have to be careful of, or just errors in our channel, which can introduce noise. So it actually turns out that because we're using quantum states, an eavesdropper will, if they were to try to gain information, introduces detectable errors. And it's in such that our protocol has a certain error threshold that we can more or less monitor. So if our errors are above the error threshold, we can say, okay, we have to stop our protocol, it's not safe. But if our error is below the threshold, then we're good to go. So how this translates when we start increasing the dimension, so you can see here, the previous example was with polarization. Obviously, we want to have some form of a positive secret key rate so that Alice and Bob can actually transmit a key. And how this scales with the cube error, the quantum bit error rate. And you see this goes to 0 at around 11%. So this means that in 2 dimensions, Alice and Bob can tolerate up to 11% of errors. You can see as we increase the dimension of our system, which we could do using OAM, that we actually push this error threshold higher and higher. And as well, we increase how much information we can actually optimize that. So at the end, we increase our information capacity and we increase our noise tolerance. That's one of the advantages of going with a higher dimensional encoding scheme, as you can see here. Okay, so that's the basics of QKD that I want to concentrate on. Now we can go into some of our fun experiments that we've done. Caution, if you do not like the cold, or if you enjoy sleeping or are afraid of spiders, yeah, don't do QKD, it's not for you, at least not outside. Okay, so this is actually dating back a couple of years now, where we wanted to see how well can we accomplish QKD with OAM in a free space environment. So you can see here, we actually went up to the rooftops of 2 buildings that's on the campus of the University of Ottawa. So this is our Telfer building, so business, and then one of our residences. You can see here, we went to Home Depot, we got some plywood, we built ourselves some boxes. Very, very sophisticated. And on the inside, you can see we have our breadboards with all of our optics on it, and just enough room to fit actually 2 people in the box. Yeah, to have a bit more of a schematic look, what do we have in these boxes? So Alice can prepare her single photon which is produced by SPDC. She can prepare it into a particular structured state using a series of wave plates and a Q plate that Felix talked about, and then she can send it across the room. Bob correspondingly can make a measurement using Q plates and then detect it. So what do we get in the end? Well, first thing we noticed, spending all those nights to the roof, we have the problem of atmospheric turbulence. So what this is like you'll see if you look at stars or planets on certain nights, they start to twinkle. This is due to atmospheric turbulence. And it's this concept that we have these different sizes of what we call Fried cells in the air. So these are different pockets of air with different refractive indices due to pressure and temperature, and that actually deflects parts of our beam. And so what we end up with is, even though we started with, say, a nice Gaussian or a nice OAM looking beam, we end up with something that is not nice to work with. So you can imagine that this introduces quite a bit of errors. So after a lot of trying and a lot of trying, we actually eventually did manage to get results that were below the error threshold. In this case, we're using a 4-dimensional system. So you can see down here, we have mode 1 and 2. These are actually vector vortex modes. So it's a combination of polarization and OAM. And we managed to accomplish a Q pair of 11%, which is below 19%. In comparison, we wanted to see, okay, so how well would the BB84 be if we went with a 2-dimensional system instead? So even though we got a lower Q pair, this actually corresponded to a lower key rate. So there is some advantage to using a high dimensional system. Okay, so that was all well and good, but now, as any good experimental physicists, we want to push ourselves. So we upgraded ourselves from this 300-meter link on campus to a 5.4-kilometer link in collaboration with the National Research Council of Canada. So this is one of their buildings on their campus at on Montreal Road. And you can see we upgraded from boxes to a nice luxurious shed that we can now stand in, slightly warmer, but yeah, a lot more space. And so this is kind of in progress of testing and stuff like that. But now we're actually armed with new toys that we can kind of combat atmospheric turbulence with. One of them being so a scintillometer. So this allows us to actually read out how strong the atmospheric turbulence is. But then we also want to integrate an adaptive optics system, which will then mitigate or correct for any disturbances or perturbations that we get from atmospheric turbulence. So you can kind of see that kind of scheme here. Okay, so moving forward, we can now move to an underwater experiment. We kind of got tired of going up to the roof, and we're like, okay, let's go to a pool instead. So note, there is now mosquitoes instead of spiders. Can't get away from the bugs. So you see here, this is our first experiment that we ran a couple years ago now. So this was actually based in one of our previous PhD students' parents' pool. So that was a lot of fun to bring our equipment there, but we didn't stop there. We actually went and tried this at the river. We had a bit of trouble there because of particles in the water. And so we asked the NRC, hey, do you have a big flume tank? And we're like, okay, try this. But we'll just concentrate on our first experiment in the pool. So unlike air, we have a much different transmission window for water, which kind of limits which wavelengths we work with. So usually in free space, we use the infrareds or the visibles. But with water, we need to be working around this kind of blue-green window in order to get any sort of significant transmission range. Now you might say, okay, you have 200 meters, is that really good enough? And for some applications it is, and it would be useful. You can see here, we'd have no hope to use kind of telecom wavelengths. And now we have additional problems of scattering if your water isn't clean. Okay, so pool party with QKD, you can see here, this is our nice pool that we had. But again, the mechanics or the parts of it are the same working infrastructure as we had for the free space case. We have our nice sender, so we have our single photon source where Alice can then prepare a particular state. Here, instead of using a Q plate, we used a spatial light modulator. So I don't think Felix introduced that, but it's just, you can think of it as an LCD screen where we have control over each pixel to introduce a phase. And then on the reverse side, we have a receiver with kind of a mirror sort of setup. So just like in the free space case, we're still dealing with we're still dealing with turbulence, but now it's underwater turbulence. And if this is playing, then everyone can see, you can kind of see our mode dancing and deforming. And we can actually characterize how much deformation we have by decomposing our wavefront in terms of Zernike polynomials. So they give us a kind of a physical intuition of, okay, how much is my beam tilted or tipped or spherical aberrations and such. So for water, predominantly we had these two orders, which were astigmatism. And one of the other effects that we noticed in this kind of stronger turbulence regime is vortex splitting. So over time, what we saw was the singularities of our beam actually splitting and lensing. So this adds another bit of error on top of when we try to do our experiment. So this phenomenon is actually also observed in free space, but we did not, at least for our previous free space link. So results, we tried different dimensions. You can see here are different MUBs. Here we just use purely OEM as opposed to structured light. You see here, so for 2D, we were below the threshold, 3D below the threshold, 4D, and it just, too many errors. And you can think of this as because when we start using our higher order modes, our mode is actually larger, so it's actually seeing more perturbations across its wavefront. So bit of success and a lot of hope going forward. So with the success of that experiment, we're like, okay, let's let's try this in an even more real environment. A pool wasn't quite good enough for us, so we took all our stuff, rented a cottage. You can see our nice beachfront real estate that we had, and set up some breadboards on the beach and sent the water. Here, unfortunately, we thought we could go further because now we were using the right wavelength, but there was a lot of algae in the water. It had rained a couple of days before, so we could only really achieve about 5 meters, where optimally we could maybe get 100. So if you're interested in those results, I encourage you to go check out the paper listed here. And just recently published was our work with the NRC. You can see here a large water flume tank. There's me sitting on it. And here we went and probed again, okay, what happens if we used our vector vortex beams? What happens if we use different distances to more rigorously do it? Now we don't have mosquitoes to worry about or particulates in the water. So if you're interested, go check out that paper. Okay, so with that, this was by no means a one-woman team because, well, we need an Alice and a Bob. So I'd like to thank, obviously, everyone at the SQO team, in particular Fred and Felix and Robert, obviously our PI, Ebrahim, and all of our collaborators at the NRC, at Max Planck, that helped us a lot. Yeah, funding, of course. So thank you. Any questions?
Okay, thank you very much, Alicia. I think Katie has one question from YouTube.
Right now.
Can you read out the question? I don't have.
Okay, Katie's question is for interaction beam, for interaction-free imaging, can the wavelengths be separated? Can you detect visible photon via imaging in the terahertz, for example?
So I think that's targeted at Felix, so I'll let him answer that.
Yeah, I'll let Ebrahim interrupt me, but I believe it hasn't been experimentally shown yet, but I think the current idea is that this is determined by the pump beam. So the wavelength of the pump beam will determine kind of your resolution there. So in that way, you can't kind of steal some advantage by going way out into a degenerate case where you pump one really short wavelength and one really long wavelength in each arm. But that's a great question, and it has yet to be shown, I think, experimentally.
Yeah, okay, thank you very much, Felix. I think I got notice that we should wrap up now since it's already 11 o'clock here Pacific time. So we will have a break for about half an hour, and we will return to the panel discussion at 1:45 in East Coast time. And there you can hear many discussion about, let's say, the career path for physicists. And during the break, I will encourage you to, let's say, take advantage of the poster session, and you can chat with your peers, and you can find many of us there. And there's also career fair taking place in Gathertown. So hope you enjoy them, and we'll see you after the break.
just one ping only facility.
Hi, Paul and Jan and Sandy. How are you guys doing? Awesome. Can you hear me okay?
Can, but you've got some weird echo going on.
Okay, let me fix that. All right, how is that? Yeah, sorry, we've got a few different computers set up in here for the different technology. It's good, thank you. Lovely, so we will get started hopefully right at 2:15. Just so you're all aware, this is being streamed to YouTube, and it is also being streamed to GatherTown, which is this kind of like live 2D world that the participants are at, kind of like a conference center. So pretty exciting. And yeah, anyway, I will be watching questions on the YouTube chat and asking them in here. So you're you're going to be interacting with me.
And each other, presumably.
Yeah.
We can't see our
it's
lovely
fine.
audience.
Awesome. So that's done. Yeah. I got 3 here. All right, so it is 2:15 and I am very excited to get us started with this panel. So good afternoon and welcome to the panel, Where to Go After Finishing a Degree in Physics. The goal of this session is to provide students and other conference attendees with insight from 3 distinguished individuals with very different non-academic career paths. And here we have with us today Paul Webster, the General Manager and Chief Technology Officer of IPG Photonics Canada, Sandy Ikes, Director of STEM Learning at Science World, and Jan Florianchik, the Senior Data Scientist at Netflix. Now, in a moment, I will have each panelist give a brief introduction of themselves, and then we will open the floor up to questions. So that's how this session is going to work today. And a reminder that since there is a delay between the Zoom call and the YouTube stream, you're encouraged to ask questions in the YouTube chat as soon as possible to ensure that they are answered in a timely fashion during the session. You are also able to ask questions via GatherTown. Our canPOM administrator will be copying questions from canPOM over to YouTube, and I will be monitoring the YouTube chat. So without further ado, I will invite our first panelist, Paul Webster, to give his introduction. Go ahead, Paul.
Thank you very much, Kate, and thank you very much for inviting me here. So I have been in Canada for my full university life. I did my undergraduate degree in engineering physics at Queen's. Sorry? Oh, okay. So I did my undergraduate engineering physics degree at Queen's. And at that time, I was thinking of getting into the nuclear power industry. And a summer spent working there between years convinced me that was definitely not the right answer for me. So while I was in my last year of my degree, I saw James Fraser give a presentation on a new imaging technique that was described at the time as ultrasound with light instead of sound. And that sounded really interesting to me, and that was basically enough to get me started with a graduate degree with him, which eventually became my PhD, and where I developed a technology to adapt this idea of ultrasound with light instead of sound, called OCT, to an industrial application. And we didn't really understand how big of a deal this was at the time, but it turns out that there's a lot of people that want to know how deep a laser weld penetrates in real time. And as we started to put the pieces of this together, we realized it'd be time to patent the research and start a company. So in 2012, about a month after I graduated my PhD, or defended my PhD, I started this company, LDD, with another individual here in Kingston. And shortly thereafter, we started to add more Queen's students to the fold. And operated that company selling a device that measures the quality of laser welds. We operated that independently until 2017, almost exactly 3 years ago, when we were acquired by IPG Photonics. So today we are the Canadian arm of IPG Photonics Corporation. They're the largest producer of fiber lasers in the world, which is the preferred technology for welding and cutting of metals with lasers. And we operate a branch here of about 32 people that work in my group, specialized in continuing to develop this technology and other related technologies, photonic technologies primarily, to support advanced manufacturing applications. I would say just a couple highlights on the things we work on today. The vast majority of our work right now is related to e-mobility, which is the industry term for electric vehicles of all kinds. And this ranges from, of course, the cars you're familiar with, but extend to rail devices, so trains. And there's even a group that is trying to make a lithium-ion powered cruise ship, which you wouldn't have expected as being the kind of thing you do with lithium-ion batteries. But all of this stuff requires very fast, very precise joining technology, which lasers are well suited to do. It's about the fastest thing you can do to put these things together. So that's one of the areas where we specialize in right now, but we also have applications in medical devices, in lots of other automotive applications, defense, there's a lot. But if it's expensive and it's made out of metal and you're going to make a lot of them, you probably want to get a laser involved at some point in time. So that's the beginning on me, but I'm happy to answer any other questions you might have for the panel.
Wonderful. Thank you so much, Paul. And next up, I will invite Sandy to give her introduction.
Hi. Oh, it's so exciting to be here. Is James Fraser what we all have in common, Kate?
It very well might be.
Between the three of us, not with Jan.
Oh, okay. Oh, that's fun. So I did my undergrad in physics at the University of Waterloo back in the dark ages. I did a little bit of research in summer terms and that kind of thing, and was looking forward to a career in grad school, career as a researcher. I came out to the West Coast, to Vancouver, to go to Simon Fraser University, which is where I did a master's and a PhD. My work was I think what would now be called computational physics. I don't think there was a particularly good name for it at the time. So I was running models of leaky optical fibers on a computer, which is probably less powerful than my cell phone is right now, and trying to figure out if it would be a good idea to make logic gates out of that kind of system. It turns out that that's not a good idea. So I can't say I had a glorious graduate school career, but I did get a PhD. Throughout that time, even starting in high school, I was working with various science communication and science education organizations, sort of off the side of my desk. So in high school, I went to school at the Ontario Science Centre, had a part-time job there for ages, took a teaching degree while I was doing my undergraduate degree. So I always had one foot in the kind of teaching education world and one foot in the research world. And as I was finishing my PhD, the person who was the most likely to take me on as a postdoc was describing the kind of day in the life of a researcher in his lab. And he was talking about 10 hours a day, 7 days a week. And I suddenly came to the perhaps not amazing revelation that there was absolutely nothing that I wanted to do 10 hours a day, 7 days a week. I knew amazing people who loved their research so much that they would have done it all their waking hours. I was not that person. It was kind of a hard thing to realize. So I was looking around for other kinds of work. And because I had some background in science communication and teaching, the timing was exactly not right for me to get a job at Science World in Vancouver. So that was like almost 25 years ago. The timing was exactly not right because I was a good year away from finishing my PhD, but I took the job anyway. I'd be happy to tell you about that kind of trauma, finishing a degree while working full time. I've been at Science World ever since, but my job has changed an awful lot. So Science World is a medium-sized science center, not as big as the Ontario Science Center, kind of comparable to Sudbury's Science North, if that's something that's more familiar to you. We have a province-wide mandate. We do outreach all over British Columbia. Actually, we do outreach all over the country right now because we can't stop people from signing into our stuff from everywhere. And I've been doing different things. So I've done some exhibit design, not the actual design work, but the conceptual design and the content design for exhibits. Programs. I've built exhibits about fuel cells. I built exhibits about pop music. I trained science professionals in Turkey. So I've done a whole lot of really cool, exciting things, all kind of under the umbrella of informal science education. It's a super cool job. Over the years, the nature of the organization at Science World has shifted a little bit. So I have a management job now, but it's also not the kind of work where you can ever really be purely in management. You wind up, going to a strategy meeting 1 hour and the next hour you're teaching preschoolers about gravity wells or something. So that's me. Happy to talk about that in whatever direction you wish to go.
Wonderful. Thank you, Sandy. And last but not least, I will invite Jan to introduce himself.
Thanks. Hi. My name is Jan. What should I start with? I started with a PhD in physics and mathematics at McGill many years ago. And coming out of that, I found an interesting project in quantum computing with a professor named Patrick Hayden, who was in the computer science department, although it was a very sort of physics related field, and ended up sort of sneaking my way into a computer science department as a physicist that way. And because my research from that point on kept being in quantum computing, I was sort of a theorist. I ended up slipping into an electrical engineering department for my PhD at the University of Southern California in Los Angeles, which is where I am now. And about 2 years into that PhD, I realized that I was pretty sure I didn't want to go into academia, and that I wanted to find something else. Notably, one of the reasons being that quantum computing jobs in Los Angeles, where I wanted to stay, are mostly Department of Defense funded, which means they're restricted to US citizens, because you have to get some sort of secret clearance. And the year, 1 year before finishing my PhD, that summer, I did an internship as a data scientist at a identity fraud company down in San Diego. And it was a really great experience, completely different from grad school, and very fulfilling. And when I came back in the fall to finish my PhD, I sort of like surprised my advisor, like he thought he had lost me. So I came back in the fall. He's like, "Oh, you're gonna finish?" I'm like, "Yeah, of course." And I had a sort of a happy coda to the end of my PhD. And after that, found work as a data scientist down here in Los Angeles, first for 2 years as director of data science at a mobile gaming company called Scopely. There's a lot of data that you can analyze from mobile games, so that was the work there. And for the past 2 years, I've been working in content demand modeling at Netflix, where we work on a variety of weird and interesting questions about audiences and the kinds of shows that they like. And it's been that ever since.
Very cool. Awesome. I guess, well, thank you guys, first of all, for giving your introductions. And again, really pleased that you're all here and have so many different experiences that you can talk on. I will open the floor up to question and answer now. So if you have questions, again, a reminder to please post them in the YouTube channel. And if you are on GatherTown and you'd prefer to ask questions there, you can direct those at the canPOM moderator in the auditorium podium. But aside from that, I have a ton of questions for you guys, so I can keep us here all day. I won't. But I guess my first question is pretty broad, but I'm mostly curious as to what made you decide to choose the career path that you're on. Like, was there a moment that you kind of knew that this is what you wanted to do? Did you sort of just follow a bunch of steps and sort of wind up where you are? I guess, yeah, I'll leave it open-ended there, and feel free to step in. Yeah, Paul, it sounds like your mic is off.
Yeah, so I can give you a little bit of background on that. For me, I'd come up with a very specific idea, a technology that was not proven, but seemed like it would probably work to solve this problem. And I realized that I was really interested in getting the answer to that question. And a lot of the time you figure, well, you get answers to questions while you're doing your degree, you're doing this research. But there are another level of questions that can only really be answered once you do it, quote, for real. And that's really one of the main driving factors for me, was to take it to that next level and start to ask, does this seems like it works in a lab? Your definition of what is real kind of evolves as you go through your academic life. I mean, for a master's student, it's real if you can do it once, and a PhD student, it's real if you can do it twice. And then in the manufacturing world, it's real when you can do it millions and millions of times, and have it still work. So it's another whole level, and there's this aspect of product development and team building and things of this sort that is still necessary to make it, to realize it. And leaving the academic world and going into the commercial space, where you can get investment, and people are only going to do that because they can make money off of it, right? So that was necessary to take my baby and let it grow up. So that was one of the main driving factors. It also just seemed like the best idea at the time. It wasn't like some grand overarching plan. Most of these decisions are made on the margin.
Fair enough. I feel like a lot of people can relate to that. I guess, Sandy, your mic is off, so do you mind chiming in?
Yeah, no problem. I can sort of tell this story two ways. So sometimes I tell the story as in, I knew I always wanted to be a science museum professional. That's what I did at the end of high school. It's how I spent all my, all my summer jobs when I had a choice. I can tell it that way. I don't think that's actually very true. I think I just kept a lot of doors open. And when I had to jump, when I had to make a decision about what I thought was going to make my impact in the world the most significant and also give me the best chance of a really rewarding and fulfilling life, I looked at the options that were available to me. I was really privileged to have those options available to me, right? I wasn't in a position where I had to do one thing or another in order to make money or to, fulfill some other requirements. So I had the options available to me, and I said, well, I like research. Research is fun. I'm enjoying it quite a lot, but I want to be able to do a bazillion other things. And I know that I can do fantastic teaching. I know I can make a great impact that way. And then every time I've needed to make a decision since then, I've looked at that like, am I still making an impact? Am I still making a difference? Does the world still need what I do? And I guess the last year has been pretty rough. But if nothing else, it's proven to me that the world needs folks that can bring the general population along on the science bandwagon. Every time I see misinformation campaigns, I say, yeah, the world still needs what I do. So it feels pretty good to be involved in that. I don't know what it would have been like if I'd followed a research career, but I know I'm still getting a lot of reward from doing what I'm doing.
Awesome. Thanks, Sandy. Jan, would you like to share your insight here?
Sure. I think my answer is less romantic and maybe more personal. I finished my undergraduate in 2009, which was a year into the Great Recession. And staying in academia at the time was a great way to insulate yourself from the worry of having to be on the job market. And I had also grown up in Ottawa with my father working in the photonics industry, in the early 2000s, from that sort of boom and bust cycle. You can remember Nortel and things like that. And so I had not to get too real, not to be a bummer, but I had this real instilled fear of okay, if I'm not the best in the world at doing, I don't know, quantum computing or black holes or whatever this passion was, I want to find something that I know is versatile, and I know I want to find something where I don't have to I can get immediate feedback about the value that I provide to my employer. And that's a weird thing to go after. It feels monetary or transactional, but it's a place I get satisfaction. And since then, I've been able to sort of rotate a data science career towards the topics that I enjoy. So working in the entertainment industry, it's fun. I enjoy it, and I think it's great. But I get to do it, the day-to-day practice of it is a type of work that I feel very secure in, and the sort of investment and reward cycle is much faster than some of the other things I've tried in my career. So I just want to make room that that's a possible motivation. It's maybe too real, but yeah, it's not very romantic.
No, I think it's totally legit to make decisions based on what's going to give you the security and the comfort that you have to live a decent life. I mean, that's, there's no sense in living a risky life just because it sounds more romantic.
Fair enough, fair enough. I think, yeah, again, good advice for students who are trying to figure out what to do with their lives. Definitely for me, at least, so hopefully I can speak for multiple. We do have some questions coming in now. The first is for Jan. This might be a quick one, but can you tell us any sneak peeks for shows that are getting greenlit or canceled at Netflix?
No, I cannot. End of answer.
Thank you. That was a very succinct answer. I will move on to the next one, which is directed for Sandy. How crucial is graduate experience in becoming a science communicator? What level of the administration should we consider reaching out to if we're interested in such a job?
I think I don't think graduate school is crucial to being a science communicator. I think in my profession, you have more credibility if you have some kind of direct research experience. And I know that my employer uses my PhD for that. It was the side skills that I learned as a graduate student that helped me to build those kind of chops. So you have to be able to get up and talk in front of an audience. You have to be able to make complicated ideas clear. You have to be able to write. It's a very different audience. But I also, like, I have a best friend who did a master's degree in physics, and she actually liked writing her thesis better than she liked any other part of her research experience, which is just plain old weird. But that convinced her that she wanted to go into technical writing as a career. So I think it's those side skills. Nobody's using what I learned in my PhD research. Nobody's using that, not for any purpose, but I'm certainly using my confidence in that I understand how science research works, or at least I can understand how science research works, and I have a little bit more credibility. You can now get degrees in museum education. You can get degrees and diplomas in science communication, and those are fantastic. I still don't think they're necessary. Like, I don't think you have to have that credential. Laurentian University has a science communication program. UBC has a museum education program. Those are not sufficient. They're handy, but not sufficient. I think the business that I'm in has become more professionalized. So I didn't have anything official other than an Ontario teaching degree. When I'm looking to hire people, I'm not looking necessarily to hire people who have credentials as a museum educator, as a science communicator, but I am looking for people that have science smarts and who look like lifelong learners. And so those are the qualifications that I'm looking for in hiring people, that they're curious, they communicate really well, they're comfortable translating complicated information. It's easy to expect that if you have a lot of science education, that somehow you're going to be hired at a very high level at a science center or something like that. I wouldn't go out there and expect that. Because the skill set is quite different. The graduate degrees are valued, but in my business, it does not get you better pay or a higher level position. You still have to start by talking directly to the public. That being said, I know my colleagues who have research experience come with a better set of side skills and more experience in the business. So it's kind of tricky, right? I know people come in and say, I have a master's in museum education, I want your job. And I say, well, give it 15 years and you're going to need to start by making oobleck with 12-year-olds.
Thank you, Sandy. I have a question now for Paul. If somebody has an idea that might turn into a startup, how the heck do you deal with uncertainty of going out on your own?
In one sentence, you accept it, because there's nothing more certain about a startup than uncertainty. And anybody who's in an early stage startup in 2020 will probably have a tale of woe to tell you about that. When I got into it, I think the thing that helped me be more comfortable about the risk was probably ignorance of it. That is, you just don't think about it too much. It'll drive you nuts if you're thinking about that all the time. I looked at it from the beginning with, initially I didn't think that I had it in me to become an entrepreneur, and it took a person inside the commercialization office at Queen's to kind of tell me, no, you could probably do it. And not only you could probably do it, this is how we can get some money together to actually build a company. Once somebody who should know gave me a vote of confidence, and I was able to see how we could even begin to start a company that way financially. The last point I had in my mind was, well, it probably will fail statistically, like that's how these things go, but at least I'll have a nice CV line to go after. And I knew I could get other jobs with my degree in the photonics industry And at least I would be, if nothing else, building my own brand by trying to promote this company, so that if the company didn't work out or it got sold for parts or something like that, it would still not, it wouldn't be a shame on my resume. Lots of people have companies that fail. The fact that you went out and tried is not going to be a mark against you. I guess the last point is, if you're not going to do it right out of school, I think it just gets a lot harder. Unless you're independently wealthy and you become independently wealthy later on, you can fund your own startup. I mean, I guess that would make it easier. But most people, their lives tend to go in an arc that makes starting new companies harder as time goes on. Because when you're out of school, you're giving up nothing to go start that company on your own. You don't have a job right now. But if you go and take a job, and 10 years later you've had 10 years of experience and the perks and pay that comes along with that, deciding to throw that away when you may even have a family you're supporting to then go out on your own, that's a much harder call than I had to make when I was just leaving school. So I think it's knowing who you can trust, who's able to provide you advice at the school, I think would be really, really helpful. There's some pretty important rules about how patents work that you really should understand. I think a common thing I ran into when I was first starting off is, very early in the conversation, people would ask me if I have a patent on this idea. And they're asking it for a number of reasons that I won't get into in great detail here unless somebody wants to ask about that. But you should make sure that during the process of you trying to publish as much research as you can to get scholarships and impact factors, if you really do want to try and commercialize this, you could have undone yourself by some of the things that are incentivized with the normal academic track. So there are some relatively simple things you can do to protect yourself if you really think this is commercialization is a real outcome, but you have to do that first before you present the paper, before you go and show it to everybody you can possibly think of and say, hey, hire me, I've got this great idea. So the tech transfer office at your school hopefully will be able to help you with some of those details. And if not, maybe Google can too. I don't know. Haven't tried it recently.
Interesting. I guess just to follow up on that then, when you first had your idea, were you thinking of publishing, or were you kind of drawn to the patenting path earlier on?
So I had a narrow miss with publishing it. So my very first paper that I published as a first author, I wanted to put a particular sentence in that paper, and James Fraser didn't let me do it. So I thought we would be able to do this thing in this sentence, but in his words, like, we haven't proven that we can, and so we can't put that in the paper. And I'm so thankful that he shot me down, because had I put that sentence in that paper, I probably would have removed my ability to patent the idea. And it would have changed, or at the very least, it would have limited the kind of patent that I could have gotten in a way that I wouldn't have liked it. And so, yeah, so I did publish, but thankfully I left out the most important piece, and was able to then later on commercialize that part of the idea. Just by luck, not by planning.
Do you remember the sentence? Would you be able to share it?
Oh, relatively speaking, it was saying that I could apply this idea to welding. So at the time, James knew nothing about laser welding. I mostly knew nothing about laser welding. But it seemed to me that if you can do it for this kind of process, you should be able to do it for that kind of process. And that's why I wanted to put it in there, because I figured it would be significant if you could do that. And there's, looking back, I think there probably is room for something like that in like a discussion section of a paper. But again, just lucky. And there's so many other just lucky like bullets in the story of LaserDev that I could regale you with. But that's a lot of it, is like moving from one lucky moment to the next and trying to avoid the most unlucky moments. There's nothing certain there. There's no fixed trajectory. You hear all about entrepreneurs and their pivots. I mean, those things are real. You don't pivot because it's comfortable. You pivot because if you continue on your current course, there's complete disaster. I mean, Netflix is one of like the most famous pivots there are in the business world, from renting DVDs to online streaming, right? So those examples are all around you.
Wow. Well, thank you, Paul. And I guess on that note about Netflix, I have a question for Jan now. And I'm so glad someone asked this because it has been kind of burning in my head. But people keep talking about this data science. What exactly is data science? Is it mostly MATLAB and Excel? How easily does a physics PhD kind of port you into that type of career?
Yeah, I love that question. Thank you for whoever asked it. And also, my apologies to whoever asked the previous question about Netflix. I didn't mean to be curt. I wish I could give you something. The the reason I can't tell you that is Netflix is a remarkably transparent company internally. And I also really enjoy working there. And those two things just raise the hair on my neck when someone's like, can you please leak secrets? And I'm like, I don't want to misspeak because I really like working there. But so let me also assuage your fears about transitioning into data science. I'm on a team of 10 right now. Half of us are ex-physicists. And from all over physics. There was, I think that's 2 astrophysicists, 1 condensed matter. There's me. It's the breadth, the full gamut. The thing I think is a lot of people focus on with data science is the specific shortcuts and techniques and skills. So they'll be, do I learn Python? Do I learn R? Do I stick with MATLAB? Do I go with Excel? By the way, you should, if you can, learn Python and SQL in like a weekend because they're not terribly hard. I know ORAD will hate that I said that it's learnable in a weekend, but I really do think that the sort of the trade of it, the actual coding, is the simplest skill to learn, especially if you're in an academic setting and you're used to picking up things rather quickly, like very complicated concepts. These things are the actual sort of things you do with your hands, quote unquote, is simple. The things that are more complicated and that it is valuable to have an academic degree for are the way you communicate and the way that you have a nose for what's valuable. You have a nose for understanding which question to answer using sort of the quote unquote least amount of work, but that'll still result in the greatest impact or the greatest amount of revelations. So one example, and I live by this maxim from my master's advisor, is especially in theory, but I guess the same must be true in experimental sciences as well, is you want to pick questions that, or you want to pick theorems that you either know you can prove or that are going to be so wrong that the answer is interesting anyway. And like, I think that is a core nature for scientists, is to pick the question that gives you the most divergent path and gives you like the most interesting contrast in what you're finding. And that's been true in my career in data science as well. And also there's a lot of impact you can have just by being the person who thinks about simple things the clearest. So I think back to my time at Scopely, the mobile gaming company, and it's a company that is organized like a publisher of mobile games with a bunch of different studios inside it that are all making their things, and the publisher sort of runs all of the technology that allows the various publishers to sort of do advertising and user tracking and all of that. One of the things that I got the most positive feedback on was a Wikipedia page, like internal Wikipedia page I wrote about the number of samples you needed to resolve a hypothesis test. It's like literally the first chapter of any statistics textbook, and there's about 100,000 blog posts written about it. And nobody went to the blog posts. People went to my page because I was like the scientific authority in the company, and it's not an underutilization, I think, of the skills. Like at the same time, I was trying to build like a machine learning algorithm to like do something, and like people are like, whatever. They wanted somebody who knew the edge cases, who knew how to hunt them down, and wanted to make sure that these things that other people are writing about are applicable here as well. And it's a simple thing at the end of the day, but it takes like the years and years of training that you're getting now to get that answer right. It minimizes the risk for the business, right? They say we don't want to farm this out to somebody who doesn't know what they're talking about. We want somebody who knows what they're talking about to tell us, even if it's a simple answer. That often ends up being the thing people come back with the most positive feedback about. There's also the other end of the spectrum where you're building more complicated things, and then it's exciting to be at a big place like Netflix because there's a lot of colleagues to learn from, and your skills get better over time. Contrast that to Scopely, where I was, I think, the only data scientist for about a year and a half. And you learn just a different set of things. Either way, I think physicists are extremely well prepared.
Yeah, and that really resonated with me when you're talking about knowing what questions to ask to get the most interesting answer. And I wonder if that's I never thought about this before, but I wonder if that's a kind of a physics superpower or a science researcher superpower that is an unrecognized useful soft skill. Just the ability to think tactically and really logically. I'm also delighted to hear that Netflix is yet another one of those places that collects physicists. I've noticed that once a physicist gets on staff somewhere, even if they're not doing physics, more physicists tend to collect in those places. And I think it's because physicists recognize the special kinds of skill sets that other physicists have, differently from engineers, differently from computer people, which I think I've always thought that was really interesting. I had a whole bunch of people my friends in Vancouver who were working for a medical imaging company, and the skills they were using they could have been physics skills, but that wasn't what they were doing. But they just kept accumulating more physicists. They had physicists in their sales department. They had physicists in their technical writing department. It sort of accumulated.
I think if you
one third to one half, something about 1/3 to 1/2 of the people in my group here are physics or engineering physics grads, and it's not because they do physics every day. It's largely because of the kinds of problems you gravitate to, and the way you like to communicate about them, and the versatility is particularly of engineering physics, being able to reach for all these different disciplines, whether it's electronics or optics or mechanical things. Those all benefit the kind of work we do in this automation heavy space.
I think it's a testament to physicists' ability to pivot. That the program I did at McGill for my undergrad was called a Joint Honors in Math and Physics, because what they had done is they had looked at the physics program and be like, hey, if you take like 4 more math courses, we'll give you a math degree. And it was the same that's true in computer science, where they're like, yeah, if you took like 4 more computer science courses, you'd basically have a computer science degree. Like there's so much commonality that the silo is very artificial.
Yeah, Waterloo had that program too, the Joint Honors in Math and Physics. And the other weird secret thing that has been a great job skill is coding, which I did. I did a lot of coding as a grad student in Fortran on ugly, great, slow computers, and it turns out that now that's a huge hot topic in education circles, and being able to support people that are teaching kids to code. That's what's kept my job during the pandemic.
Interesting. Actually, Sandy, do you mind elaborating on what sorts of things you're doing now that there is the pandemic? I guess that has to come up eventually.
Yeah, it's not a great time to be a high-touch interactive science center. We shut down in mid-March because it was chaotic and we didn't know how to keep people safe. And then there was a huge reopening project to try and reconfigure who we were, reinvent ourselves, so we have a lot more online offerings, do a lot more online teaching. I mean, this is nothing new to anybody here, because we're all doing online teaching and learning, but it's not the most comfortable place when what you're used to doing is hands-on inquiry science stuff with grade 5s, right? We have had a grant that encourages us to teach coding and computational thinking skills. So that's fantastic, because that's much easier to transport online. It's not perfect. The robots in real life are way more fun than the robots online, but it's definitely a savior. And then I think moving forward, it's just an awful lot of strategic thinking and trying to figure out how to exist in sort of this funny hybrid space of online and in-person learning. We have the science centers are open, so we have visitors coming in every day, but a lot of the things that we were doing that were quite innovative and fun involve way too many people being way too close to each other, so we're not doing that. It's the advantage, if there is an advantage, is that by heading online, we are able to reach farther, faster than we can in person. So you can visit a class in Fort Nelson, that's way up north. You can visit a class in Fort Nelson in the morning and visit a class on Vancouver Island in the afternoon. So that's fantastic. We're able to reach more different people as long as they are internet connected. But the other part of it, as I said before, is that like there is no doubt in my mind, just based on what's going on in the world, that the work that science centers do, science centers and other kinds of science communicators do to help people understand the nature and processes of how scientific knowledge progresses, how we know things. You know, why is it that in March you're not supposed to wear a mask and in August you are, like how that works? Translating that for people and being a trusted place that ordinary people can go, people who may not have had a lot of access to academia. That work is really, really important, and I feel good about that. Like I feel good about that in a way that I'm not sure I would feel if I were a purely entertainment venue or a movie theater or a bar. Those things are all important, but like I can see every day that the world needs science education. So that's the good thing. The kind of sucky thing is that we're down half our staff and we're all tired all the time, and we wash so much Lego. Like, oh my God, so much Lego washing has happened in the last couple months.
Oh man, washing Lego. I would not have expected that was yeah, that was ever a thing.
It wasn't on my kind of, mid-career management path. I was not really counting on having to wash giant sacks of Lego, but whatever, I wash the Lego and think what I'm doing is very valuable because people are learning science.
Oh, that's fantastic. I'm gonna shift gears and direct a question over to Paul now. You mentioned academic habits going against what's best in the startup space. Could you comment more on this as well as the role of patents?
Yeah, so what I was referring to is that generally speaking, the mission in the academic space is to publish as much as possible as soon as possible, because that's what gets you impact. If you're not first, then it limits what you can publish, in some disciplines at least. And in the commercial space, there does tend to be a value in a certain degree of complete secrecy about some things, and in other things where you don't want to be completely secret, you may want to protect them legally through patents. And if you follow the academic compass completely and publish as much as you can right away, it certainly removes the complete secrecy option. And in many cases, it removes the patenting option. So you won't be able to build a foundation for commercial value on those two things. Now, that's not to say there are no good businesses without secrecy or patents. There are many good businesses that you can describe that don't have those things. But in the technology space, especially when you don't have a mountain of cash and an army of lawyers to protect yourself, sometimes patent might be a cheap asset that you can develop early on without a whole lot of time and effort and money. So that's the tension that I'm referring to there. But I think there is a middle way. Lots of people have successful academic careers, at least through their PhD, and maybe even on to being professors, and still get to patent and commercialize their research. But it has to be done deliberately, and it's instead of accidentally. I'm the example of accidentally doing it right, not the thing you should aim for.
Awesome, thanks, Paul. I have another question that is directed at everybody, but maybe I'll have Jan answer it first. What types of skills, abilities, and personal attributes are imperative for your work in your fields and your specific career? And how did you learn or acquire these skills?
Sure. So aside from the hard skills we've been talking about, which if I'm going to throw out 3 keywords, learn Python, SQL, and Git, and you're set for most data science jobs. Another is, I think, thinking about risk correctly. You have to understand what risk you are managing for the organization you're working in, and how you're responsible for it. So one example is if you write, if you do a type of analysis, you're the one who has to cross the T's and dot the I's, and you have to be thorough there. But you don't necessarily have to be thorough about certain other things, right? Like people probably won't care about whether your shell is configured correctly, or if you have the most beautiful code. If it's not code that's going to be shared with anybody else. So so understanding that is, I think, really, really useful. And another one that has come up again and again, just as sort of like I'm a little, I think I still find myself early in my career as a data scientist. It's been 4 years, and it says senior, but that's, doesn't make me feel senior. Another is how you take feedback. I think depending on how your academic career may have gone, you may have gotten very direct feedback, which you may have accepted very well, or there may have been a drought of that. And asking about feedback and pushing your people around you to be more honest about helping you improve is very, very important. It's a difficult thing to ask for if you don't have that that skill developed. They're both soft skills, but they're like really critical for having a good velocity in your career.
Yeah, it's also very difficult if the culture of your organization doesn't support the showing of weakness, right? If you figure you're in a rat race and the guy next to you in this conference could be getting that next promotion instead of you, and so you're not going to speak up and say that, yeah, I don't understand this. That's not something you necessarily have a lot of control over unless it's your company. But having a culture of openness and exposing yourself, exposing your ignorance, I think if you do it the right way to the right people, it can come off really well. I try to be, I get hit with a lot of things from people all the time, and routinely someone will say something in a conversation that I have no idea what they're talking about at all, but I go right at it. Like I just say, I have no idea what that means. Can you please explain it to me? And if you're coming from a place where you've got a PhD and you should know all the things, that might not feel very natural, but try it on for size. There's still lots of things to learn and appear ignorant about, because that's how you're going to get it filled in.
It's so interesting to me to hear that response, because I immediately wrote down, so that I wouldn't forget, I immediately wrote down curiosity and humility as the most important characteristics for the kind of work I do. So I'll characterize it broadly as informal education or science communication. To be curious enough, like to be confident enough, of course, that if I read it and I figure it out and I ask enough questions, I'll get it, whatever it is. It was vaccine development at one point this summer. I needed to know about that. So being able to be curious, but also being able to be humble and realizing that, it's easy to go into teaching thinking that what you're going to do is bring enlightenment to the masses. That's a really comfortable place to be. Like, I know this stuff, I'm going to make everybody else know it, but recognizing that the people that are learning also come with really important insights, really important understandings of the world, really important stories about the world, and being humble enough to sort of take that on and figure out where your best meeting place is. That's something I will be working on until the day I die. I'm sure of it. And I think it's a hard thing to learn. It's a very hard thing to learn as a physicist, honestly, because you spend a lot of time faking it till you make it. At least I did. Being tough and looking the stuff up in the dark at night so that nobody would know you didn't know. But that humility, that ability to be curious and to learn from people who don't have PhDs in physics, I think is a hugely important characteristic of people that are good at science communication.
Yeah, so Sandy, to your point, I see why that's maybe something difficult for somebody who's gone through physics, but there's another aspect that I think flips it the other way. I look at it as a central tenet to like the physics ethos, this ability to be able to go back to first principles and always be able to explain how you know what you know. everybody should be able to do that all the time. And this is so important when you're discussing complex technical topics, especially when there are known gaps in everybody's information. Because until you can have that honest, like you can take that challenge. How do you know that? Like what tests have you done? What data do you have? What is that based on? You're a group doing the things that physicists love to do should be talking about that kind of stuff every single day. And you should be thinking about that internally, like always looking for that weakness in your argument, always looking for that gap in your understanding. It should bother you when you're soaping yourself in the shower. Like that's a sign that is a sign that you're thinking about the right things, because we are all so weak as individuals, and it's only when we can like openly discuss those weaknesses or the possibility of weakness and understanding that you can try and develop something greater than where you're at right now. I'm sure this is not limited to our fields, but
yeah. I certainly did not experience that culture in graduate school, not at all. The culture I was in graduate school is you didn't show weakness because you would be eaten alive. And I'm hoping that that's changing, but yeah, I'm hoping that people that I think both of you probably are the next generation compared to me, but the reality was, yeah, you showed weakness, you would get eaten. So I'm hoping that that's changing, because I agree the best part about physics is the continual questioning, the continual bringing it back to first principles, always trying to figure it out, and always the back and forth with other clever minds.
Yeah, let me just sorry, before you get into it, there is a kind of like a limit to this, though. I want to draw in there, which is, I think it's great to ask these kinds of questions and be able to respond to them. But ultimately, the responsibility of learning, like filling in one of these gaps, is your own. And so when you're dealing with your colleagues and asking them to fill in these, like help you out these things, you have to make sure they know that that it's your responsibility, it's your job, and you're not just relying on them relentlessly to help fill in those kinds of things. They will want to help you because they want to succeed as a group. But if they have to start repeating themselves many times to you, you've asked the same question 6 or 7 times, or even thrice, you may have some own work to do on your own before coming back to the group again. And that you just have to temper your curiosity with that kind of a limitation. Sorry, Jan, please go ahead.
Oh, no worries. I wanted to dovetail from your thing about bringing things down to first principles as like a core tenet that physicists live by. There's 2 ways that shows up for me in data science. One is often when you're building a model, you're just looking for like what other inputs or features have I not thought of that could be useful in the model, and like so much of my work is like predicting how a curve lands that I'm like, I'll just put more derivatives of the curve, which is like apparently a novel idea to computer scientists, but for physicists, you're like, no, it's the Taylor expansion. It's like we've been doing this since like electromagnetism 101 or whatever. But the other way that it shows up is in my role at Scopely, since I was like the one data scientist at the company, there would be a lot of vendors that came through. Trying to sell various business-to-business or B2B solutions to that company. And my role in a lot of those meetings was just kind of to hammer them on, like, they were like, oh, we take your data and then we train 1 million models on it. And I'd be like, why? Like, you should just be doing 1. This is insane. And asking those questions, like, it's the drive towards be like, no, there should be a clear path from first principles to what it is that you're selling me. And it melts away a lot of people's sales pitches down to like, you understand the true value of what people are trying to sell you because you understand the mechanism behind it and you can see the real value.
We do a lot of, under normal circumstances anyway, a lot of visitor research. So watching people learning stuff in the Science Center and deciding which are the most effective tools to help people learn what they're learning, when they're learning. And one of the fun research skills is asking the question, well, first of all, what are you going to do with this information once you've got it? So I'm kind of annoying for asking that question all the time. But the other one is like, is the thing you're asking about actually showing what you think it's showing? And I think coming from a physics background, my standards for what means proof are quite high. It's kind of weird to be in the social science research space occasionally, but you know, just because somebody is doing this thing, or just because you get so many of these people doing a certain behavior, that kind of thinking is super valuable in my job.
I think, okay, that's good. I think we lost you a little bit at the end there, Sandy, but it looks like your connection is still here. Awesome. Now, I am cognizant of time. We have 5 minutes left in the session. Before we end, I think it would be great to end off with one final question for everybody. And I would really love to know what the best part about your work is. Yeah, what do you love about it? And maybe I'll pass it off to Paul first, because your mic is on.
Yeah, this was maybe one of the greatest surprises for me in the entrepreneurial journey. One of the best parts is it's not the money, it's not the technology, it is building a team and seeing people follow your lead, see people learn from you, see people exceed you in the things they're specializing in, and grow their careers and their lives in the same building that you all get together. I'm like every day it's a bit of a cliche to say, like, I'm honored that people continue to choose to work in my group. They have these are people that can go work lots of places and be very successful, and they continue to choose us, and that is a great feeling. And I had no idea that existed when I was in the physics department. Surely, like, stories like that played out in the physics department, and graduate supervisors, I'm sure, get a bit of that all the time. But that was one of the most surprising and the most rewarding things, is to see this team grow and continue to better themselves and better the product.
Thank you, Paul. Jan, can I ask you to step in next?
Sure. I'll give you the funny one. I'll give you the real one. Last year, I was walking through the lobby of the Netflix building, and I made eye contact with Sandra Bullock, and I had to go sit down because it was so exciting. She's amazing, and that's the only thing that's really happened there. But the real one is the only thing I love more than building things is watching people use the things I've built. And I built ultimately, like, I build software, so it's not even a physical thing, but to see somebody use that software or read out from it and then ask me things about it is extremely rewarding, because you get this sense of ownership that is just really, really great. So I love that.
If I can just add to that one, sorry, Sandy. So there's a similar one here when you get to see a particular car driving down the road, and it's like, oh yeah, there's a little bit of me in that. That's fantastic.
Well, I get literal love letters from some of the people whose lives I touch. They send pictures, and we love you, and the kids are fantastic. But I think the part of my job that I think brings me the most lasting joy is working with teachers who will say things like, I never knew I could code. I certainly never knew I could teach coding. And then when we started doing, it happens with other topics too, but it's just been most recently with coding. When we started taking on teaching coding, and I had junior staff saying, there is no way we can ever do that with children. Like, there is absolutely no way. And then 6 months later, they were saying, this is my very favorite thing to teach ever. It's a variation on watching people use the amazing thing you built. Watching people walk into an exhibit where you were the content designer is fantastic. You've created beautiful, fun learning tools, and people are like, they hug them. It's fantastic. So yeah, and we're all talking about creativity and seeing the results of our creativity, which is, honestly, that's not what people told me when I was going into physics.
Oh, some really great answers. Honestly, thank you to all three of you so much for joining us today and sharing all of your fantastic insights. I know I had such a blast with this session. And I think I can speak for others when I say that they probably did too. So yeah, again, thank you so much for being here. And I guess now we have a break coming up for the next half hour. We'll be returning on the same platforms at 3:45 p.m. Eastern Time. And we will be returning with the next research showcase, which is Professor Christa Brosseau's group from St. Mary's University. And they'll be taking us on an adventure in plasmonics. And our conference organizer, Danielle Tokars, will be chairing this session. Over the break, I encourage you to take an advantage of the career fair. It started up on GatherTown, I think 15 minutes ago. So definitely go talk to some of the people running the booths. I know Paul's company is there, so you can go and chat with IPG. And yeah, with that, I will let you all go and take your break, and we will see you in the afternoon session. Thank you so much, everyone. Awesome. And Sandy, Jan, and Paul, we are still on YouTube, so I'll keep it short. You're more than welcome to stay on the call if you'd like, but at this point, you are free to leave. If you want access to GatherTown or YouTube or anything, let me know and I can send links.
Yeah, I'd booked in until 3:30 on my calendar, so if there is anybody else has other questions or things, I've got until then at least that I can continue to talk.
Okay.
I'm actually also curious in how Jan got connected to the whole group. How did you?
So I don't know Jonathan Fraser. Or Jason.
James.
I don't. James Fraser. I did my undergrad with ORAD.
Oh, okay. So ORAD knows James, and as a result, I met ORAD because of James. So that's that's the full connection.
James married one of my buddies from residence. Actually, I think James was at the residence too. So like, yeah, he's an old buddy. Yeah, and I really want to know if you are part of the brain behind predicting Netflix preferences.
I'm not part of the recommendation team. They're all up in the Bay Area. Down here, it's more the Hollywood side of things. But you should totally send me if you get bad recommendations, you can send it to me. I don't know. I might have somewhere I can paste them.
I had this awesomely 21st century argument with my daughter who was using my Netflix account to watch Friends, and I said, like, for God's sake, if you're going to use my Netflix account, use something that I'm, don't screw up the AI with your bad taste.
I'm still, by the way,
we got young children, and we play children's videos on our Netflix.
Oh yeah, that would
predictions.
I bet it does.
So like, I told my wife that she's spoiling my Netflix. This is ORAD, by the way.
Hi.
Hi, ORAD.
Hi.
Echoey.
I'm very echoey.
Do you want to come on here?
Well, I just want to say I yelled at my wife for screwing up my algorithm, and she's like, "Who says that? Screw up my algorithm."
We all do.
It was really lovely to meet you guys. I have to run to another meeting. So thank you very much for having me, and please stay in touch.
No worries. Thank you so much, Jan.
Good to meet you all. I'm gonna run away too. I'm doing family things.
Sounds good. Thank you, Sandy.
Bye.
Take care. Bye-bye.
Awesome. How are things going, Paul?
All right. Well, good. Yeah, we just closed a really big order, so we're full up for the rest of the year and trying to put it all together and thinking about Christmas time, I guess. Kingston's pretty quiet as usual.
Yeah, that's what I've heard.
Not a bad place to be in the pandemic, but
yeah. Just as long as you don't go to any nail salons, it sounds like.
Yes. Yeah. Well, that was, it really dashed my hopes, to be honest. I was all booked up, and then coronavirus came along, so
darn.
Those sequins are just not going to sparkle the way they usually do.
No. Can find another dream.
Yeah.
Awesome. Well, I won't keep you too long. You are welcome to stay on, but I'm sure you have other stuff that you need to get done.
Yeah.
Sounds
all right.
good.
Bye, everyone. Thanks very much for the invitation.
Awesome. Thanks, Paul. Have a good day.
Bye.
Hi, Krista. That looks really good. Hopefully you can hear me. I'm not sure if you want to also try your audio.
Sure, Danielle, can you hear me now?
Yes, that sounds good. Thank you.
Thank you.
Hi, my name is Danielle Tokars, and I'm an assistant professor in the Department of Chemistry at St. Mary's University. I welcome you to the third research showcase of the day. Just a reminder that anytime during the talk, please feel free to ask your questions through YouTube. It is my absolute pleasure today to introduce my colleague, Dr. Christa Brosseau, and her talented students. Dr. Brosseau received an honors bachelor degree of science in chemistry from Dalhousie University. She then completed an MSc degree under the supervision of Professor Sharon Roscoe at Acadia University, where she studied the absorption of proteins on metallic surfaces using electrochemical methods. She then completed a PhD at the University of Guelph under the supervision of Professor Jacek Lipkowski on a project which involved using electrochemistry and infrared spectroscopy to probe the interaction of cholera toxin with a model biological membrane supported on an electrode surface. Afterwards, Christa moved to Evanston, Illinois to take up the prestigious Andrew W. Mellon Foundation postdoctoral fellowship at Northwestern University under the supervision of Professor Richard P. Van Dyne in collaboration with the Art Institute of Chicago. This project used surface-enhanced Raman spectroscopy to analyze colorants in historical textiles and paintings. In 2009, Christa joined the chemistry department at St. Mary's University as an assistant professor, was promoted to associate professor in 2014 and full professor in 2019. Christa is also currently the Canada Research Chair in Sustainable Chemistry and Materials. Today, Dr. Brosseau will be discussing her adventures in plasmonics from sensing to sustainability. Christa, we all look forward to hearing your talk.
Thank you so much, Danielle, for the introduction, and thank you to the organizers for the invitation to come here today and speak to you all. So, of course, I'm going to be doing a very short introduction to our research, but it's really my students, Kaylee and Carolyn, who will be leading the show today. So, our group is really interested in plasmonics, and it's really exciting for me to be able to talk to the Canadian photonics community today, because I know that many of you are working in plasmonics or have some experience in plasmonics. And just, very quickly, for those of you that may be new to plasmonics, we're really interested in the unique electrical and optical effects that occur when electromagnetic radiation interacts with nanoscale metals, and certain nanoscale metals in particular. And this oscillating electric field, this incident electric field that oscillates, causes a collective oscillation of conduction electrons in these nanoparticles because they're trapped. They're quantumly confined in nanoscale dimensions that are shorter than the wavelength of light that's used to excite them. And so that sets up all kinds of interesting effects, including the beautiful colors you see for red, gold nanoparticles, and also enhanced electromagnetic fields at the surfaces of these particles, which we exploit in surface-enhanced Raman. So we'll be talking a lot about surface-enhanced Raman spectroscopy today. So just very quickly, where are we from? So we're located in Halifax, Nova Scotia. So St. Mary's University is the second largest research university in Nova Scotia after Dalhousie University. And we're located in the city of Halifax on one city block. And so everything is really nice and compact. And we have really excellent research, and the chemistry department is no exception. So I invite you to come visit us in Halifax someday if you're ever in this part of the world. So in our research group, we are interested in a broad range of plasmonic applications. So we kind of span this plasmonic sensing regime. A lot of what we do is looking at point of need and point of care sensors that are developed using plasmonics. And so surface enhanced Raman spectroscopy, for example, being used to detect biomarkers and biofluids that could be characteristic of a certain disease state, and also looking at environmental contaminants in, for example, natural water systems. A lot of what we do is in the sustainable realm as well. So we're interested in biodegradable plasmonic sensors, trying to move away from plastic sensors, for example, and look at more environmentally sustainable sensor platforms. We have a lot of interest in plasmonic catalysis as well as earth-abundant plasmonics. And so that's not something you hear too often, but in the plasmonics field, we have to start thinking about this because the majority of plasmonic work right now is done with either gold or silver, and both of those metals are expensive, and they both are facing earth abundance limitations in the next 50 years if we continue to use them at our current rates. And so we're interested, for example, in the plasmonic properties of copper, which has a lot of promise theoretically, but is challenging experimentally. We're also interested in bio-inspired plasmonics, and this idea really takes a cue from nature. So if we're trying to order nanoparticles or nanostructures over a large length scale, that's very difficult, but nature does this fairly well. So if you think about structural color and physical structures that provide color, we can take advantage of those kinds of structures to build plasmonic sensor platforms. And so you'll be hearing about a lot of this today from both Kaylee and Carolyn. So I'll introduce Kaylee first. So Kaylee is a honors Bachelor in Science and Chemistry student. This is her honors year. And Kaylee has been in the research lab now for several years. She just completed her third NSERC USRA. And Kaylee has been looking in the past at electrochemical surface enhanced Raman spectroscopy. And in particular, we've been looking at trying to develop that as a tool for identifying and detecting bacteria. So she'll be talking about that research today. Followed by Kaylee, we have Carolyn. So Carolyn Farling is a current master's in applied science candidate in the chemistry department at St. Mary's University. And Carolyn will be talking to us about her research, which is really looking at upcycled food waste as potential bioscaffold materials for developing SIRS substrates. So with that, I'll turn things over to first Kaylee and then Carolyn to present our research group.
Hello. So I will share my screen. All right, and hopefully everyone can see that. So I'm going to be talking about electrochemical surface enhanced Raman spectroscopy, or EC-SIRS, as a tool for bacterial detection and identification. And so to start, pathogenic bacteria is a real issue in our community in mainly the fields of our food and our water supply. So pathogenic bacteria is bacteria that can cause human illness and lead to very serious diseases. And so what we need is an ability to detect bacteria at the point of need so we know when water is safe to drink or food is safe to eat. And so currently, there are some methods for bacterial sensing, such as PCR, colony counting, or ELISA. Now, with each of these methods come their own limitations, whether they be time-consuming, expensive, or not appropriate for point-of-need analysis. And so with that, our group put forward Raman spectroscopy as a potential option for bacterial sensing. And so Raman spectroscopy is a vibrational tool. It's used for fingerprinting a molecule based upon the way that it inelastically scatters monochromatic laser light. And so when you illuminate your sample with a laser light, the majority of light scatters in a way known as Rayleigh scattering, where there is an elastic scattering taking place. But some of the light scatters in a Stokes or anti-Stokes pattern, which is inelastic scattering. And so when this occurs, there is a unique vibrational signature produced for the molecule that is scattering that light. Unfortunately, though, Raman spectroscopy on its own is a very weak method with only 1 in every 10 to the 6 photons being Stokes shifted. And so to combat that, we use surface enhanced Raman spectroscopy, or SIRS. And so the way that SIRS works is you place your analyte of interest now onto a metal substrate, and this greatly enhances the signal as well as quenching any fluorescence by the metal. And so the laser excitates your sample, and then it scatters the light through Raman scattering. And so when this occurs, the enhancement is amazing. So it moves from every 1 in 10 to the 6 photons being Raman scattered to 1 in every 1 photon being Raman scattered. And so to show you visually just how great this enhancement is, you can see here on this plot 2 signals for the same molecule, one collected using normal Raman, which is the black line on top, and then one collected using SIRS. And so you can see how clear these peaks now become that were otherwise hidden using normal Raman due to the weak nature of this method. And so with our project, we want to try and use SIRS by placing bacteria on the surface of nanoparticles and testing to see if we can illuminate the bacterial membrane with a laser and generate a sample for that bacteria using SIRS. But unfortunately, currently in the literature, there's big issues with using SIRS for bacterial detection because you get these weak, irreproducible signals that aren't very characteristic to the bacteria that you're looking at. And so why is that? Well, when you take a closer look, what's happening is the bacteria are undergoing a stress response in these conditions next to the nanoparticles, and they're actually moving away from the surface and essentially freaking out in solution and releasing all of these breakdown products and lysing their membranes. So these metabolites that come out are what's actually being detected because they're now closer to the surface of the nanoparticles that are getting that SIRS enhancement. And so you can see these 7 metabolites that are released into solution. And so that's what's causing our issues we see with bacteria in those difficult to differentiate between strains, weak spectra, and irreproducibility. So we tried electrochemical SIRS or EC SIRS. And so in electrochemical SIRS, we make a synthesis of either gold or silver nanoparticles using acetic growth solution approach that gives us near monodispersity. And so then we apply a voltage to these screen printed electrodes. And on the working electrode here, you can see that we place a drop coating of our nanoparticles, and then we place our analyte onto that working electrode, place it into our spectrometer, and apply the potential here using a USB potentiostat. And so with that, we're able to influence the way that the analyte absorbs onto the metal surface and change the signal that we're receiving. And so here's just an example with adenine. You can see we start with an open circuit potential and then set it to 0 volts and then move down in increments of negative 0.1 volts, all the way down to negative 1 volts. And you can see that all the way along as we change the way that that interaction occurs, the signal becomes slightly stronger and stronger. And so for this molecule in particular, the best signal is at -1 volts. That's not necessarily always the case, but we do always do the full progression to see where the best signal comes out. And so here we characterize the breakdown products of those 7 nucleotides that are released by the stress response of the bacteria near the nanoparticles. And so you can see the bottom line here is all 7 of those combined into one spectrum. And so with that, our method looks like growing the bacteria on a nutrient agar plate for 16 hours at 37 degrees Celsius. And then we just remove one of those colonies and place it into a liquid nutrient broth. And we let that grow for 16 hours as well. And then we centrifuge and wash the bacterial pellet that grows within the nutrient broth. And we then place our electrode that has our silver nanoparticles onto into a vial with that bacteria. And so we ended up going with silver nanoparticles for this project and a 780 nanometer laser line for our Raman spectrometer. And so we chose that based upon a comparison of both gold and silver, as well as a laser line of 532 versus 780 nanometers, and found that that gave the optimum signal for our analytes. And so here you can see the EC SIRS results of E. coli K12, and you can see in this SEM image that E. coli is falsely colored in red on the surface of our silver nanoparticles, so you can see its presence there. And you can see that the best signal we're getting is at -1 volts with the most intensity of the peaks. And so then you can see here a similar result with B. megatherium. You can see the rod-shaped bacteria present on the surface is much larger here than it was with E. coli. And again, the best signal is coming out at -1 volts. And so with that, we had some suspicions that that signal we were receiving was, as I was saying, a result of those breakdown products, but we wanted to get more support for that statement. And so repeating that experiment again, I inoculated the bacteria in my nutrient broth and allowed that to grow overnight, centrifuged the bacteria and washed it with phosphate buffer. And then I added the bacteria to the vial with the phosphate buffer solution as I typically would. And normally at that step, I would add the electrode and allow that to incubate for 6 hours. But instead, I did not add the electrode in this study, and I just simply allowed the bacteria to sit in that phosphate buffer solution for 6 hours and release any breakdown products that they may in that time. And so after that time period had passed, I syringe filtered using a 0.2 micrometer pore size syringe filter, and you could visually see that the vials appeared clear after filtering out the bacterial cells. And so I selected a 0.2 micrometer pore size based upon characterization of the size of my bacteria under SEM. And so following that, I put my electrode into the now filtered solution of the phosphate buffer and any small metabolites that may have been released into solution, allowed that to absorb onto my surface, and then performed EC SIRS on the electrode. And here's what I saw. So you can see that through SEM, there are no bacteria present on the surface anymore of the silver nanoparticles, but we're receiving the exact same signal. And so these results really support the claim for us that this is coming from the metabolites released and not from the bacteria's membranes that are on the surface. As well, you can see we receive similar results with B. megatherium. Again, no bacteria are present in our SEM image, but the signal remains the same as previously seen with the bacteria present. And so here you can see a comparison. On the left, we have E. coli K12 and the signal that we are receiving for that in our typical experiment where the bacteria are present. And then you can see a comparison to each of the different breakdown products individually, as well as all 7. And the same for B. megatherium here. You can see B. megatherium on the top and the 7 breakdown products, as well as them all combined. And so comparing our result for each of the different bacteria experiments to a database of these breakdown products, you can see that there is a % match associated with the signal received for E. coli in each of the breakdown products. And so interestingly, the signal is unique to the different bacteria in the amount of those metabolites that they release. So for example, in adenine, you can see that E. coli has a 35% match with adenine, whereas B. megatherium has a 74% match. And so that's interesting because you could use those results to then characterize if bacteria was once present in your, say, water sample, but you couldn't verify that it is still present. And so metabolites may be good, but membranes would be better for us. And so membranes of bacteria can be either classified as gram-positive or gram-negative. And so taking a closer look, gram-positive bacteria has a thick peptidoglycan outer layer. And an example of this is B. megatherium that we worked with. And then our model gram-negative bacteria was E. coli K12. And so you can see that this has an outer membrane with lipopolysaccharides on the outer surface and a thin inner peptidoglycan layer. And so those differences in the membrane components would lead us to expect to see differences in the signal that we receive if it is indeed the membrane that we're looking at. And so we try to functionalize the electrode to promote more bacterial adhesion, hoping that if we had a greater density of bacteria present on the surface, then we could actually see a signal for the membrane. And so I tried pyridine, adenine, and cysteamine. And so with adenine, for example, I chose that because it's one of the metabolites that's released by bacteria in these stressful conditions. And so that would be advantageous for the bacterium to move towards and adhere to in solution, because a site that has a lot of adenine present would indicate that there are nutrients available for the bacteria. And so I drop coated these onto my electrode and then placed it into the bacterial solution to incubate and absorb. And so does this increased bacterial adhesion allow us to detect the membrane signal? Well, unfortunately, not really. It did give a big increase in the amount of bacteria present on the surface, but unfortunately, the molecules we selected for to try this with all have very strong Raman signals. And so even if they did give us this increased adhesion, their signal is just so strong that we can't see anything else but those molecules at the moment. And so what about forgetting about doing the electrochemistry and trying something completely new? So I tried to make a silver colloid, and then I actually made silver nanoclusters by aggregating my silver nanoparticles using a sodium chloride solution. I continued to inoculate the E. coli, grow that overnight, and then I filtered that E. coli through a 0.45 micrometer cellulose nitrate membrane, rinsed that with phosphate buffer, and then filtered my silver nanoclusters on top of that, and did SIRS and SEM following my SIRS of the filter. And so you can see that on the filter, there's a large amount of bacteria that are captured by the 0.45 micrometer filter. And so the bacteria are mainly located where the holes are in the filter funnel. And so you can see that here where the hole is, it's very interesting. You have a very thick layer of bacteria present. But when you're actually looking outside of that darker area on the filter and just on this white area, you can just see only the cellulose nitrate under SEM. So I just thought that was a very interesting result. And so looking at the SIRS signal, it is strong and uniform over the filter paper on those darker spots. And we do see these two peaks coming up that are consistent with the membrane components that we would expect to see of E. coli. And that does give us some hope. But overall, even with repeat washings, the signal still seems to mainly be dominated by those nucleotide breakdown products. And so with that, it remains a mystery, but we've made some progress and supported some of our hypotheses in where these signals are actually coming from. And so I want to say a big thank you to the Brosseau research group and as well my mentor, Taylor Link. This was originally her honors project, and after passing it along to me, I spent 2 summers on it. And I really enjoyed the project as well. I want to say thank you to my co-supervisor on the project, Dr. Clarissa Sitt, as well as NSERC and Nova Scotia Research and Canada Research Chairs, and everyone else for funding, and you all for listening today. So thank you.
Thank you so much, Kaylee. That was a really great presentation. So one of the questions we have, I think I'm going to direct it directly to Dr. Brosseau. So the question is, can you elaborate on EC SIRS? We are not familiar with the physical microscopic mechanism and would like to know more. Where are you applying the voltage and what is it doing? So Dr. Brosseau, if you could give us more of a general picture of the microscopy technique.
Yeah, for sure. So thank you, Kaylee, for that great presentation, and thank you for the question. So we do get this question a lot because, you know, many people have seen lots of SIRS talks, but you might not have seen a lot of electrochemical SIRS talks. And that's kind of our niche areas because we have background in plasmonics and SIRS, but I'm also an electrochemist. And so being able to put those two together is really useful, actually. And it's useful for SIRS because when we do SIRS, we're normally doing that on either silver or gold because those are the best plasmonic metals. And those are already sort of good working electrode materials for electrochemistry. And so essentially when we do electrochemical SIRS, we're doing spectroelectrochemistry. So we are able to change the applied voltage, and it's applied directly to the nanoparticle film. So we have the nanoparticle, silver nanoparticles or gold, depending on what we're doing, on top of a conductive carbon layer. And so the voltage is applied directly to the metal surface, the plasmonic metal surface. And so what we're doing as we change the voltage is we're changing the surface charge of those particles, which is really helpful because for SIRS, it's very distance dependent. So the surface plasmon is localized to the surface. If you can't get your analyte within about 5 nanometers of that nanoparticle surface, you're not going to benefit from any of the SIRS enhancement. And so if you can't get your molecule onto the surface, forget about it. You're sort of sunk already. And so by applying a voltage, we can manipulate the surface charge, which allows us to influence adsorption of the adsorbates, which is really helpful. And it's particularly important for silver. You know, everyone who does SIRS on silver, but silver actually as a metal, it has a very negative potential of zero charge around -1 volt. So that means when you're working with silver under open circuit conditions, it's very it's very positively charged. And so that's not a great a surface charge for lots of adsorbates. Most neutral molecules will prefer a neutral surface charge. And so as we step the voltage, we're able to manipulate the surface charge. And so it's very useful for SIRS because it gives us another handle by which we can influence adsorption and therefore get either a stronger signal or a signal at all. So as you saw in Kaylee's presentation, sometimes we don't see anything at open circuit potential. And if you're just doing regular SIRS, you're always stuck at open circuit. And so being able to apply a voltage just gives us an extra handle that we can use to influence the adsorption.
Thanks, Christa, for that. There's one more question by Alexander Harper. He's asking if you could clarify what you mean by silver nanoclusters. Noble metal nanoclusters should produce an extremely strong fluorescence response, which may interfere.
That's right. So noble metal particles can have a strong fluorescence, but noble metal particles like silver and gold actually have the ability to quench fluorescence. And so very close to the surface, the fluorescence is quenched. And so this is very useful for systems where there may be a lot of inherent fluorescence. Which for normal Raman is always a problem because fluorescence always wins. And so when we're doing SIRS, sometimes we can have fluorescence interference as well, but the noble metals help to quench fluorescence very close to the particle surface.
Thank you, that's great. All right, so I think now we'll move on to Carolyn Farling and her presentation. And just as a reminder, please feel free at any point to enter any questions in the YouTube chat.
Okay, thank you. Let me just share my screen. Okay, so as they said, my name is Carolyn. I'm a master's student in Dr. Christa Brosseau's group at St. Mary's University. And today I'll be telling you about a piece of my master's project where I'm working with silver films over bioscaffolds as SIRS substrates from upcycled food waste. So Kaylee gave us a great introduction of SIRS theory, or surface enhanced Raman spectroscopy theory, but I'm just going to emphasize a few of those points again. So the SIRS enhancement mechanism depends on the nanoparticle size, shape, and positioning. And what I mean by that is once we coat a substrate or sensor in silver, each silver nanoparticle enhances the electromagnetic field locally around itself. So when two of these particles are positioned closely together, you get the overlap of this electromagnetic field enhancement between the two particles. And we call that a hotspot. So the closer you can get your analyte or target molecule to this hotspot, you're increasing your chances of being able to get a clean signal or even detect it at all. But SIRS signal enhancement isn't as simple as just coating any surface with silver. So here I'm showing you on the left silver on glass, and glass would be a smooth surface at the micro scale. And you can see from the black spectrum that I'm showing you here, there's no characteristic peaks for the molecule that I'm looking for. It is a relatively flat signal altogether. And this is because glass is a smooth surface, and we've learned that having a rough surface increases your signal because of the way that the nanoparticles are positioned. So on the right, I'm showing you silver on a peacock feather, and you can see that the feather is very rough on the micro scale. And I have a characteristic peak in this red spectrum here for my molecule. So rough surfaces are better for hotspot formation. Thus, these surfaces are preferred for nanoparticle scaffolds. So some of the first substrates that we're working with this idea of if we roughen a surface or we use a rough surface to deposit our silver, then we are going to get better enhancement would be silver fons or silver film over polymer nanosphere. This is which I'm showing you on the left. And you can see the polymer nanospheres in the first image here are very symmetrical, evenly distributed across the surface of the sensor. But then in the second image below, they're showing you some of the limitations of using a silver fawn. The silver is actually not as evenly deposited as we originally thought, as well as the polymer nanospheres are not evenly deposited across the surface either. And this can be kind of a difficult substrate to prepare for these reasons. Also, I'm showing here silver film over cleaved mica. So this would be a silver film over just a basic mineral. And there is some surface roughness compared to just over the nanospheres, but once again, it's irregular, kind of amorphous on the micro scale or the nanometer scale here. And this would be a problem because this clear spot where there are no nanoparticles present would be kind of like a dead spot on the surface. So you're not going to get any signal enhancement from that area, which could increase your variability, your spot to spot variation, and just affect the reproducibility of your sensor. That's why bioscaffolds are an exciting idea to this effect, because nature has already created these really rough surfaces for us to deposit our silver upon that are already evenly ordered and neat and don't have any fabrication struggles and to that effect. So some of the more popular ones are insect wings, including butterflies, dragonflies, cicada, etc. So here I'm showing a butterfly with ridges, struts, ribs on the nanoscale that creates this rough scaffold for the silver to deposit upon. And in the spectra below, you see that all the spectra are exactly the same. And these spectra would have been taken from different spots along the wing. So that has very low variability for their target molecule here of rhodamine 6G. Similarly, flower petals have the same nanostructure or structural color. It shows up as this iridescent gleam to the naked eye that maybe is best shown in the mussel shell in this photo here, that gleam. And once again, the rose petal in this example has micropelae at the micro scale, and this is increasing the roughness and creating a better scaffold for the silver to sit upon. And high reproducibility here in the spectrum for, once again, rhodamine 6G. And then finally on the right, as I briefly just mentioned, I have a mussel shell that again has surface roughness and structural color at the micro scale, and led to very reproducible spectra for the molecule rhodamine 6G. Our group has already discovered a few bioscaffolds that are successful. So the red spectrum here, the damselfly wing, the oyster shell, the blue spectrum, and the green spectrum of the buttercup petal pictured here to the side, this yellow flower. And these three spectra have a better signal for our target molecule than the silver fawn or the silver film over nanosphere that I introduced on one of the first slides. And it's better because some of the major peaks are a bit more intense, and also there are just more characteristic peaks, especially in this 200 to 800 wave number range. And then on the right, I wanted to talk about my methods a bit more before I keep going. I use a physical vapor deposition instrument, or a PVD. And the way that this works is I take really high purity silver pellets and place them in a boat inside of the vacuum chamber here. Then when I close the chamber and drop the pressure, the silver heats up and is vaporized, and any substrate or bioscaffold that I put within the chamber is going to be coated with silver. So there are some limitations as well as advantages of these bioscaffolds. So the advantages are they're structurally stable and environmentally benign because you're taking them directly from nature. They have this 3D hierarchical structure. And as I described in the beginning, maximizing the number of hotspots or the way that the silver is positioned is going to be essential to maximizing the strength of your sensor, the sensitivity of your sensor. And this 3D structure is giving you more of a chance of creating these hotspots. There's also a hydrophobic effect of drop coating your sample in water on the surface of these bioscaffolds, because the water will bead and concentrate your analyte to that spot, which once again would just be increasing your sensitivity. And they're also cost effective and simple fabrication. Like I was saying, developing a silver fawn or film over polymer nanosphere can be time consuming and kind of difficult at times. Whereas putting my substrate taken directly from nature into a PVD and coating that with silver is relatively simple. The disadvantages, however, are the sustainability and supply. For example, the buttercup petal yellow flower that I was showing you only blooms 1 month of the year. So I have to decide how many of these substrates I'm going to need and how I'm going to deal with storing them. And that just creates some disadvantages. There's also ethical considerations from using insect wings, especially like how are you going to source the wings and are you disrupting the ecosystem by sourcing this product, as well as scalability. Again, the wings, the wing is already a set size, so you can't scale it up if you wanted to. So the ways that I'm addressing these disadvantages for using bioscaffolds is by using food waste that's compostable, that is available in large quantities and not seasonal in any way. And one of these substrates that I find the most interesting is Atlantic blue mussel shell. So I'm showing you here on this slide that the Atlantic blue mussel shell actually has 2 different surface structures that's due to having 2 different calcium carbonate polymorphs. The first one being aragonite, which is outlined in blue here for spots 4, 5, 6, and 7. And the second one being calcite, that's outlined in 1, 2, 3, and 8 here on the side. And you can see that the crystal structure between these two differ, and it really affects the surface roughness. And then interestingly enough, I found that aragonite is actually a superior surface roughness to calcite. First, I'll talk about how I know that these are aragonite and calcite before imaging with the SEM. There's about a 10 nanometer shift, 10 wave number shift here in this, around 700 between aragonite and calcite. So I can determine which crystal structure fragment I have before experimentation. And then here on the right in the rainbow spectra on the top and the bottom, I'm showing 10 different spots taken from the same fragment that is going to give me an indication of the reproducibility of my sensor and how even it is across the surface. So for the calcite, especially the bottom spectrum here, there are no characteristic peaks, and the next bottom 2 have a lot of noise. Whereas comparing these 10 trials, you can think of them as to the aragonite, we have really high reproducibility, low variability, as well as very high intensity with this 100 count scale bar here versus this larger 50 count scale bar. So then I wanted to kind of confirm this and compare this finding to other shells from edible food products. So I looked at razor clams and oysters, who are both supposed to both have mostly calcite in their structure. Oyster shell looks like this, and from all of these spots, I'm seeing the calcite that I expected to see. And the signal is definitely there, but still not as good. We're remembering that 100 count scale bar that I just showed, this is only at 10 counts, so it's less intense, meaning it's not as sensitive for my analyte. And it also had limitations of being a relatively thick shell that had some problems with the PVD. I wasn't able to fit all of the fragments into that instrument. So razor clamshell seemed like a good place to move because it is thin, but it had the worst signal of all of the shells that I tried. Very noisy, very few characteristic peaks, if any at all, in the spectra. And then finally, I did try other substrates, other bioscaffolds beyond just shells. I tried things from orange peel to broccoli leaves. And another one that I found successful was eggshell membrane. So this is a membrane that you just take right directly off of the eggs from a supermarket after you would crack it. So it is still compostable and waste. And you can see that the microstructure here is much different than the crystalline structure of the shells. It's like a fibrous netting membrane. And I'm getting great reproducibility and intensity from 10 different spots on this paper-like film that the membrane ends up forming. So that's another direction that my project has gone as well. And with that, I would like to thank the whole Brosseau group and all of our other funders. And thank you for listening. I'll take some questions.
Thank you so much, Carolyn. That was really great. So one of the questions on YouTube is, I think I missed this, but Carolyn mentioned needing to consider the ethics behind using insect wings. What kind of considerations?
Right, so considerations on where are you going to source them? Are we then going to have like an insect farm in a way? And like what regions of the world are they coming from? And also these animals are a part of a complex ecosystem. So we could be disrupting the predator-prey supply-demand sort of balance.
That
I
makes
don't know
sense.
if that helped. Okay, yeah.
Yeah, I can just add to that too. Like
Yeah, please do.
the most commonly used or quoted example is the morpho butterfly for structural color, and that's actually an endangered species. So we don't want to be, building sensor platforms based on the insect wings of endangered species. So while it's interesting to study in terms of scalability and widespread use, that's a major limitation.
That makes sense. One of the questions I had, I don't know if you have the answer to this. So one of the things that I liked seeing was the buttercup flower. I think that's such a cute idea to use that as a scaffold. But I'm just wondering, how does the spectrum change if it's withered versus fresh? Does it change a lot, or? And I know you said you did broccoli leaves, so I don't know if you saw something with that.
Right,
Yeah,
that's
so
actually, oh, sorry, Dr. Forseth, do you want to take this one?
Well, yeah, just because that sort of predates Carolyn's time, so she might not be, versed in everything that was done at that time. But yeah, it was a good question, and storage of the flower petals was something that came up right away. And so we did look at, fresh versus frozen petals, and there was some decrease in the signal. It wasn't as bad as we thought it would be. It was probably about 10 to 20% decrease in signal. So they did survive that, but we also didn't really have the right tools to preserve the flower petals properly here on campus. So yeah, so it became a sort of logistical nightmare.
That makes sense. I also really like the idea of using shells. And you had mentioned that some of the pieces were too thick for PVD. And I'm just wondering what thicknesses are optimal for using that technique, or how thick is too thick?
Yeah, as thin as possible is optimal for a couple of reasons. One, using the PVD, you have a substrate holder that's attached inside the vacuum chamber, and then you have shutters that close over your holder. So the oyster shell was too thick to even let the shutters close. So it was really more of a mechanistic PVD, logistical issue. But also it's important to have flat substrates for using Raman spectroscopy, because if you have too curved or too thick of a substrate, it changes the distance between where your laser is emitting and where it's going to be scattering off of your surface. So I would like as thin of a substrate as possible, just because it takes a lot of the complexity out.
I know in geology, they'll sometimes sand down a sample, but would that not work for you, just because then you're ruining the structure at the surface?
Yeah, geologists tell me this all the time. I haven't tried. They have all of these complicated ways of cutting their materials. I mean, I think that it would probably disrupt the surface, but I can't say that for sure because I haven't tried it.
Yeah, that makes sense. One of the ideas that came to mind was otoliths. So these are ear crystals in fish. They're actually known to be aragonite. And so I was just thinking, oh, I wonder if you've ever thought of trying that, but they're really thick. So that probably is too thick for the technique. But yeah, well, thank you so much to the Brosseau group for presenting. That was really great. Thank you, Christa, Carolyn, and Kaylee for a wonderful talk. And with that, I'm going to turn the floor over to our next research showcase.
Great, thanks, everyone.
Thank you. So I will now hand it over to Dr. Amy Stevens. She's an assistant professor in the Department of Chemistry at the University of Saskatchewan and a really hardworking member of the canPOM organizational team. She will introduce the speaker of our last research showcase.
Hello, hopefully I'm talking to everyone now. Can you hear me, Kate?
Yeah, you're good.
Okay, just checking. Okay, so thank you, Danielle, for that. And I just want to say that if anyone hasn't checked out the career fair, there's still half an hour to go, so just go and have a look at that. But right now, it is my great pleasure to introduce Professor Frank Hegmann and his group from the University of Alberta in Edmonton. His expertise is in ultrafast terahertz science, which he uses to probe ultrafast carrier dynamics in nanomaterials and biological samples. His laser research lab is state-of-the-art, and his research is very highly cited. He's also been awarded the University of Alberta McCalla Professorship, has been named the Strategic Chair in Terahertz Science and Technology, and has been recognized for his teaching excellence. So I'm very excited to hear his talk. So without further ado, I invite Frank to kick off our final research showcase of canPOM 2020.
Okay, thanks so much, Amy. That's a very nice introduction. I hope everything is coming through okay. I'll just maximize this.
Looks good to me.
Okay, so yeah, thanks again. And I'd like to also thank the organizers for, this is really cool. For first of all, inviting us to showcase sort of some of the research we're doing in our lab at the University of Alberta. But I've been listening all day to all the talks, and I was just fascinated with all the different research going on. So it's really, really quite impressive. Even the panel discussion with the people who had physics backgrounds and went into industry and things was really fascinating. And that was really a strong point of this whole canPOM thing. So nice to hear. So yeah, what I'd like to sort of showcase here is how we're using ultrafast lasers and terahertz pulses to explore ultrafast phenomenon on the nanoscale. And again, we're at the University of Alberta, Department of Physics, and just to show you, that's in Edmonton, Alberta, which is the capital. And I grew up in Ottawa, actually, and I remember, earlier on from Ebrahim, Karimi, the nice photos of the canal and stuff, so it brings back good memories. So I thought, oh, I better throw in some pictures of our city, let alone our university. So here's a picture of Edmonton. It's got a population more than 1 million. And here's the campus. It's almost 40,000 students there, just in case you didn't have a chance to visit. I encourage you to do so, and I'd be happy to show you around the labs. The Department of Physics is actually in a relatively new building called the Centennial Center for Interdisciplinary Sciences, or CCIS. And the two labs that we do a lot of our work in, ultrafast spectroscopy lab and ultrafast nanotools lab, some photos are shown here. And essentially, to put it in a nutshell, we use ultrafast lasers to explore materials. And here's just some snapshots from the various labs showing what these amplified laser pulse systems, these femtosecond laser sources look like, sort of these big, gray boxes that are worth a lot of money on this big bench. And this is sort of some of the optics that we've assembled with all these different test stations. And actually in the foreground here is some experiments that we're actually doing in biophysics, looking at the biological effects of intense terahertz pulses. So I won't be talking about that now, or neither will my two students that are going to be showcased later. But if anyone's interested, I'd be happy to talk to them about it if they want to learn more. Of course, there's been lots of people, and this is a relatively older picture, but that have been, involved in the research in here. And I just have to give credit to all the students, the undergraduate students, graduate students, and postdocs and research associates that have been involved in the research. So essentially, our research, we're interested in how light interacts with materials and how those photoexcitations that we induce in the materials with these ultrafast laser pulses change over very short or picosecond timescales, and that's the ultrafast aspect. Essentially, this is the large field of physics, of condensed matter physics, that deals with ultrafast phenomena. And what motivates a lot of this research is that there's lots of fundamental processes in materials and in nature in general that occur over ultrafast timescales. And a lot of these ultrafast processes that occur in materials also occur on the nanoscale, let alone at the atomic and molecular level. And so that's why the title of this showcase is Exploring Ultrafast Phenomena on the Nanoscale, and that is what we tried to do, one of the main research efforts in our lab. And the ultrafast lasers that we use, and in general, if you're not familiar with ultrafast lasers, they generate very short light pulses, less than 1/10 of a picosecond, or 50 femtoseconds sort of pulse duration. And they're the only tools you can use to really explore ultrafast phenomenon in nature. And the generic, or sort of the prototypical experiment that's done in most ultrafast labs around the world is called a pump probe experiment. And if you have a sample, you create a photoexcitation in the sample with one pulse and then probe it some time delayed later with a second probe pulse. So that pump probe experiment, excite and then probe, and then changing the delay between the pump and probe allows you to map the ultrafast dynamics of what's going on in the sample. And it's easy to change the time delay between the two simply by changing mirrors on optical delay stage. So one of the main probe pulses that we do, and this is part of the main focus of our research, is generating these terahertz pulses with these ultrafast laser sources. And you can see an example of a terahertz pulse. And what we can do is we can actually measure the electric field directly versus time, not the intensity. We actually measure this roughly single cycle electromagnetic transient, which is about a picosecond in duration. And that's why they're called terahertz pulses, because when you Fourier transform that, it has a center frequency around 1 terahertz. And because it's only a single cycle, it's basically got a broad bandwidth in the terahertz region. Essentially, it's in the far infrared part of the spectrum. And this part of the spectrum is ideal for looking at photoconductivity or conductivity dynamics in materials. So in other words, the transport of carriers, that's where all the action happens in that region. And Charles, the student talking later, will certainly emphasize that more. So the optical pump terahertz probe experiment, you excite a sample with an optical pulse, create photoexcitations, electrons and holes, for example, and then use the terahertz to probe the resulting conductivity as a function of time. But this is done in a non-contact way. So you have a tool that is very powerful to measure photoconductivity dynamics in materials, but without touching the material, with sub-picosecond time resolution. And a quick example here is with looking at the photoconductivity dynamics in films of silicon nanocrystals, where we not only can we look at sort of how long the carriers last as a function of time after photoexcitation, we can also sort of ask the question, well, how are the carriers moving at a certain time delay after that initial photoexcitation? So 10 or 20 picoseconds after it gets excited, are the carriers that we generated free to move, or are they more localized? And when we deal with nanomaterials, we actually expect localization effects to be dominant. And the way we sort of probe for that is to look at the spectroscopy. We actually can extract directly the real and imaginary components of the induced conductivity in these materials. And from that spectrum, from that spectroscopy, based on the model we use to fit it, we can infer what's happening on the nanoscale. So that's actually how we can probe nanoscale dynamics using terahertz pulses, at least one method. And that's what Charles Jensen will look at. And just to give you a quick idea about some of the other materials that we've been looking at, we've looked at capture dynamics of carriers in these in-gas quantum dot chains some time ago. We've also looked at materials that are being considered for solar cell applications, this iron pyrite. We're the first group to show, using this time-resolved terahertz spectroscopy technique, the observation of band-like transport, in other words, mobility increasing as you lower the temperature in organic semiconductor thin films. And the physics of that is still something that's being pursued today. Measuring the mobility of carriers that are, inside these really fragile looking nanowires, is something that the terahertz spectroscopy is very powerful to do. So in other words, it's a good thing you can't touch that because you'd break them. And so this is a non-contact way of measuring that conductivity. We've also, and there was some mention of this early on in one of the first talks today, about looking at the insulator metal transition in vanadium dioxide, and that's still a mystery in physics. But we were able to, using this time-resolved terahertz spectroscopy, resolve an intermediate metallic state at very low temperatures, which wasn't seen before. So that was really interesting work. And more recently, very new material systems can be probed. This double helix tin indium phosphide sample, or SNP, which is the first double helix material of its type, are being studied, as well as these CAD sulfide nanowire systems, solution grown in collaboration with Karthik Shankar's group here in engineering, which Charles will certainly elaborate on after this intro. But the next part is, can we directly image ultrafast dynamics in materials on the nanoscale? And the way we do that, in other words, yeah, we can, and we've developed a technique where we take a scanning tunneling microscope, which can see single atoms, but it's kind of slow, but combine it with the ultrafast lasers, which are fast, but can't get down to the nanoscale directly. And we basically couple these terahertz pulses to the sharp end of this scanning tunneling microscope tip. And the metal tip of the STM behaves like an antenna, which results in a field enhancement of the terahertz electric field at the sharp end. And that basically produces a very fast voltage transient, which produces a very fast tunnel current transient, which we can use for ultrafast STM. In fact, if we combine it with an optical pump pulse and then use the terahertz pulse to gate basically the tunnel current, we now have a technique that basically allows the measurement of sub-picosecond dynamics down to the atomic scale, which is the first time this has ever been done. And so this allows us then to directly image ultrafast phenomena on the nanoscale. And it's basically a new tool that should, who knows what we'll see. We first demonstrated this technique back in 2013 with sub-picosecond time resolution and sort of few nanometer spatial resolution, but then improved that to atomic resolution, where we looked at single atoms on a silicon surface, and we're able to image the single atoms on a silicon surface with just the terahertz pulse induced tunnel currents. And besides sort of the ability to probe down to the nanoscale or even atomic scale with sub-picosecond time resolution, the size of these tunnel currents was also a very interesting aspect. In other words, the terahertz tunnel current dynamics of an STM is something completely new. And this is something that's very exciting as well. In fact, we were able to show that these huge extreme current densities of 10 to the 11 amps per centimeter squared, we could actually send through a single silicon atom and not destroy it. And so we're still trying to understand a lot of these phenomena. So that's just a quick intro of some of the main stuff that we do. And that's why it's called Exploring Ultrafast Phenomena Nanoscale. And Charles Jensen will first talk about the time-resolved terahertz spectroscopy, and then Jesus Casada, aka Alex, will then discuss more about the terahertz STM experiments that we're doing. So I'll let them speak. Thank you.
Yeah, thank you for that great introduction of pump probe spectroscopy, especially. If we're running a little bit behind time, so if Charles can just go straight into the next presentation, that would be great. And I just want to remind everyone that please put your questions up on the YouTube channel, and I will ask them probably at the very, very end of all the talks. So put your questions up as they come in. Thank you.
Okay. Right on. Thank you for that. And thanks for the intro, Frank. There we go. I hope everybody's actually looking at the proper screen now. Give me a heads up if you're not. Yeah, so like Frank said, my name's Charles. I'm a fourth year PhD student in this group. And today I'll be talking to you guys more about the time-resolved terahertz spectroscopy that we do on nanomaterials. And I find it a good place to start is to really begin by discussing the idea in a single sentence. And Frank said this earlier, we really measure the ultrafast photoconductivity of materials. And when we break these ideas down, we can get a feel for the things that happen in our laboratory on a day-to-day basis. Ultrafast really sets the timescales we work on to around the order of a picosecond. on a picosecond, something that popped up in the chat. Let me just back out of this for a second because we're on Zoom. The presenter screen. Okay, thank you. Yes, I'll switch that quickly. Display settings and swap presenter view. Boom. There we go. Okay, so let's get to it. The picosecond ultrafast sets our timescales to around a picosecond. And to appreciate how fast these timescales actually are, the fastest thing in the universe, which is light, can only really travel a fraction of a millimeter. And on these timescales, what we're interested in doing is probing what the photoconductivity dynamics look like. And in particular, from a physics standpoint, we're interested in figuring out the microscopic models of conductivity that give rise to the dynamics of electrons and holes that we're measuring. This process is applicable to a wide variety of materials, everything from bulk crystals down to nanowire films, atomically thin materials, amorphous films, as well as some quite interesting gallium nitride nanowalls we've looked at. And to get a feel for the timescales on which we operate, let's talk about how we generate terahertz pulses briefly and how we measure them so that you can kind of get a feel for the numbers that set the resolutions that we work on. Frank showed you some pictures earlier of our femtosecond laser sources, and those laser sources are capable of producing pulses with 100 femtosecond duration and a center wavelength of roughly 800 nanometers. And when you shine these onto a zinc telluride crystal, optical rectification occurs, and as if by magic, terahertz pulses come out the other side. Terahertz pulses themselves have roughly a picosecond duration and a center wavelength of roughly 300 micrometers. The detection of the electro-optic detection that we use allows us to actually measure the electric field of a terahertz pulse. This is going to be an important part of the spectroscopy that we talk about later. But here we show a very simplified diagram of how this works, where a terahertz pulse is incident on zinc telluride with an 800 nanometer pulse at the same time. The 800 nanometer pulse is what we actually detect, and the terahertz induces a little bit of elliptical polarization into the 800 nanometer pulse, and as a result, the difference between the horizontal and vertical intensities is actually proportional to the instantaneous terahertz electric field. Now, because of this measurement, this electro-optic sampling technique, the resolution of our detection scheme is set to around 400 femtoseconds, or like Frank said, around 0.4 picoseconds. So once we have all of our terahertz pulses, we now need to figure out what we're going to do with them. And this is where time-resolved terahertz spectroscopy comes in. Time-resolved terahertz spectroscopy, or TRTS for short, is a pump-probe spectroscopic technique. So an optical pulse arrives at a sample shortly before the terahertz pulse comes through. We then repeat the measurement with a different delay, and we perform this over and over and over again, constantly changing the delay time between the two pulses. And if you're measuring the amplitude change of the terahertz pulse, because remember, we can measure that instantaneous electric field, you can map out the transient photoconductivity on sub-picosecond timescales. And I'd also like to note that this transient photoconductivity measurement is non-contact. So we've never had to touch the sample in order to probe these transient photoconductivities. But we can actually get more out of the system. At each pump probe delay time, we can measure the electric field as a function of time. This provides us with phase and amplitude information, which allows us to map out the photoconductivity spectrum on sub-picosecond timescales. Essentially, by measuring out the time-dependent waveforms, we can Fourier transform them, and by measuring the photoexcited and comparing it to the unphotoexcited state, we can extract the transient photoconductivity spectrum. The photoconductivity spectrum can be described by may be described by a bunch of familiar aspects. We may have free charge carriers, such as electrons and holes, that are photoexcited in the material. We may have excitons, which are bound electron hole pairs. We might also have electrons and holes that are free, but are localized within some nanoscale geometry. And this is going to be a key feature that we look at later on. Before we get into that, let's get some order of magnitude estimate, orders of magnitude under our belt with these terahertz pulses. First of all, their photon energy is incredibly small. We're dealing with photon energies of around 4 milli-electron volts. And when you compare that to the band gap of semiconductors, which is around 1 or 2 electron volts, the terahertz pulse is not as, the terahertz photon does not have enough energy to excite a direct gap excitation. Instead, the terahertz pulse is an excellent probe of a transient photoexcited state simply because it doesn't induce any background carriers. The durations of the pulses, like Frank was saying, are around 1 picosecond, and the bandwidth is around 2 terahertz. The center frequency is around 1.5. It is also around 1.5 terahertz. Now, for those of us that are interested in, or that have worked with imaging systems before, it's well known that the diffraction limit of an imaging system is set by the wavelength. And in terahertz, it's quite long. We're dealing with 300 micrometer wavelengths. And so the focal point is quite large. This might bring up an interesting question for the audience of, if the wavelength is so long, then how does it actually probe the nanoscale? To answer this, we look to an estimate of the diffusion lengths. And for the sake of an example, let's look at bulk cadmium sulfide, where the mobility is roughly 350 centimeters squared per volt second. If we have a 1 terahertz wave, the angular frequency is 2 pi terahertz, and from this we can calculate the diffusion length to be around 12 nanometers. So to recap, in 1 picosecond, an electron will only really oscillate at a terahertz a length of around 12 nanometers. And this sets the scale of the dimensions on which we work. And if the dimensions get even smaller than this, or even on the order of this magnitude, we need to start considering how it's going to affect our carrier dynamics. And so what I'm going to do is I'm going to give you a side-by-side example of, on the left, we'll just show you a Drude model of how a system's responding. And on the right, we'll show you what's happening to a confined carrier. An important part of terahertz spectroscopy, and one of the strongest motivations for the bulk spectroscopy, is the fact that the crossover frequencies in the Drude models typically occur within our terahertz spectrum, giving us the centered view of the carrier dynamics. So if our carriers are oscillating back and forth, and in our confined case, the box is too large, essentially our free carriers won't experience any confinement. If you then shrink the box down, our carriers are going to bounce off the ends, and we're going to see in the conductivity spectrum a suppression of the DC conductivity spectrum that was not there in the Drude case. If we continue shrinking the dimensions of it down, we expect to see even more confinement as the carriers are bouncing off the we expect to see even more suppression of the low frequency conductivity. This is a key signature of terahertz spectroscopy in these regimes, and is solely due to the nanoscale morphology of the systems. And to move on from this, I'd like to talk about some more application stuff. I'd like to talk about some of the work that was done in 2006, where our group was looking at silicon nanocrystals that were embedded in an SiO2 matrix. The difference between the silicon nanocrystal samples was the temperature upon which they were annealed. So as you increase the annealing temperature, in general, they saw an increase in crystallinity of their nanocrystals. There we go. But curiously enough, they also saw an increase in the localization in these systems. And here I've plotted the real part of the conductivity to show you guys the low frequency suppression. For reference, they used silicon on sapphire as a bulk source of silicon, and they compared that to polynanocrystalline silicon, again, which showed a little bit of suppression of the low frequency conductivities. And then they compared that against their nanocrystals, which showed even further suppression. So this is telling us that something about the nanoscale morphology is responsible for the change in change in low frequency conductivity, and it can be understood in terms of how the mobility changes before and after annealing. See, when we anneal the samples, the mobility generally goes up as the crystallinity is bettered. And as a result, the diffusion length gets larger. And so an electron that's in some confined space will feel even more confinement after annealing because the diffusion length got larger. And now I'd like to talk about some of the work that I've had the pleasure of working with in my PhD, which is these brand new cadmium sulfide nanowires that are wrapped in a two-dimensional nanosheets. The nanowires themselves have roughly 50 nanometer diameters and can be grown up to around 1 micron in length. This is a solution-based method. So all of these nanowires are grown in solution and then deposited onto substrates for us to measure. Again, this emphasizes the importance of us having a non-contact technique, because otherwise it would be quite difficult to measure the photoconductivity of these nanowire systems. In the work that we're looking to publish, that we've submitted for publication, we measure 3 different samples. We have one sample of just bare cadmium sulfide nanowires. We have another sample that's been wrapped after its growth. And then we have another sample that was wrapped during the growth. And similar to the crystallinity discussions of the previous work, we know through high resolution TEM images, we know that these samples that are grown afterward, that are wrapped after growth, exhibit larger crystallinity than their counterparts, which are wrapped during growth. And so the spectroscopic signatures that we see are going to have something to do with that. So what motivates the research on cadmium sulfide nanowires? Well, cadmium sulfide is a great optical absorber, and it was recently shown that cadmium sulfide, when wrapped in this novel carbon nitride nanosheet, when the nanowires are wrapped this way, the charge carrier transport is actually in favor of photocatalysis applications, where the goal is to turn these harmful byproducts of the textile industry into safer byproducts for ecological conservation. Some of the results we find, so let's talk about some of the results we found with the terahertz spectroscopy on these samples. The first thing we want to talk about is the transient photoconductivity. What we find in these samples is that the cadmium sulfide is our benchmark. We want to test everything against the bare cadmium sulfide nanowires. And what we find is that wrapping the samples after growth barely changes the peak amplitude of the transient photoconductivity. This means that, whereas if you were to wrap them during growth, we see a large suppression of the transient photoconductivity. This is telling us that it's likely the mobility that's responsible for the suppression of the transient photoconductivity, because the only thing that can be changed is the morphology during growth. We find that these nanowires have extremely long photoconductive lifetimes, longer than 500 picoseconds, which is in favor of photocatalysis applications, because it implies that charge carriers will have plenty of time to participate in photocatalysis. So let's look at the charge carrier dynamics. Owing to the dimensions of the nanowires, we expect to see some suppression of the photoconductivity even in the bare nanowire samples. That's because, if you recall, in cadmium sulfide, the diffusion length is around 12 nanometers, whereas in these samples, we're dealing with diameters of around 50. And so we expect to see a large fraction of carrier localization occurring. And that's exactly what we see. Our data agrees extremely well with the Drude-Smith model of conductivity. When we wrap the nanowires after they're grown, we end up with more suppression of the low frequency conductivity and more suppression of the low frequency conductivity for both wrapped samples. However, when we wrap the samples during growth, we find that the mobility overall, that is the scattering rate, the scattering time, gets even smaller. And this agrees well with our observations from the transient photoconductivity, which were implying that the mobility in this sample was lower. And now by measuring the dynamics, we can demonstrate that directly.
I just want to interrupt. Oh, you're on your summary
We're
slide.
done. Yep.
Thank you.
So in summary, we quickly talked about terahertz generation. We went through some orders of magnitude for the terahertz waves. We talked about the time-resolved spectroscopy, and I introduced you to some interesting systems that show key features of localization on nanoscale systems. And if you take anything away from this talk, it's that we measure ultra-fast photoconductivities of materials. Thank you for your time.
Thank you, Charles. That was really fantastic. I just want to ask one quick question. I think I probably missed it, but do you know why the wrapping during the growth changes things so much?
Absolutely. It's hard to pinpoint exactly why this is occurring, but from talking with our colleagues in engineering, we know that the wrapping is an electrostatic attraction. And so because of this electrostatic wrapping, it's probably going to affect the growth of these nanowires in solution, as it's just affecting the dynamics of the solvents on this, as they're trying to react and grow these nanowires.
Oh, okay, it's really, really interesting stuff, and I hope to read the paper when it comes out.
Oh, thank you.
Because we're running just a little bit behind, we're going to go straight into Jesus's talk, or Alex, I believe.
Yes. I'll stop screen sharing.
So yeah, just Alex, whenever you're ready, please take it away.
Awesome, thank you. Okay, so yeah, I'm Jesus. I want to thank the organizers for the invitation. And as Frank mentioned before, I'm going to talk about one of the systems that we have in the ultra-fast nanotools lab, which is called the terahertz scanning tunneling microscope. So first, I wanted to show you some pictures of the lab, which Frank already showed. So these are the ultra-fast lasers that we use for the experiments. You can see a picture of the inside of the laser here. And this is the STM that we use, the microscope, the STM microscope. And so what we do is basically we combine these ultra-fast lasers with the capabilities of the STM to develop this terahertz STM technique. And the question is, why are we interested in this terahertz STM system, or why is it so special? And so I think the main advantage of the system is that we can study the ultra-fast phenomena at the nanoscale. And I think at this point, this is the only technique that can simultaneously measure sub-picosecond and well, you can have sub-picosecond and sub-nanometer resolution at the same time. And so that's why it is important. And it's also very interesting because it was developed just a few years ago. So it opened a whole window of opportunities for new research to be done. And so there are a lot of unexplored areas that can be studied with this system. And so first, I want to define some of the acronyms that I'm going to be using throughout the presentation. UHB stands for ultra high vacuum. Then we have terahertz, and STM stands for scanning tunneling microscope. And so in this picture here, you can see this is the system. At the center, we have the vacuum chamber, and inside this chamber, we have the STM. On the side, we have all of these optic devices that we use to guide and control the terahertz pulses that we're going to send into the STM. And so it might look complicated, but the basic principle behind it is actually very simple. If you look through the window of the chamber, inside you will see something like this, where we basically have a very, very sharp tip. And then underneath, we have a conductive sample that we want to study. And so the way it works is we apply a bias voltage between the tip and the sample. And then we bring the tip closer and closer to the surface of the sample until we detect a tunneling current. And then we can use this tunneling current to study the surface of the samples. Just to give you an idea of the scales that we are dealing with, here we have our tip, our sample, and these are the kind of images that we can get. They are really, really small compared to the sizes that we are used to in real life. And as you can see, at the end of the tip, we usually have just a few atoms. And that's what allows us to have such a high resolution, because the tunneling current has an exponential dependence on the tip and sample distance. So that means most of the current is going to flow through the last atom of the tip. And so that's why we can have, we can detect currents in a really, really localized region like this one. And so if we then move the tip around and raster scan the surface, we can create images of the properties of the sample. And so we can get images such as this one, where in this case, we're looking at a silicon sample with a surface reconstruction of 7x7. And so that's why we see this beautiful pattern all over the place. And we can zoom in. And we can see the pattern with more detail. And every bright spot here, that's one individual atom. STM, we can resolve single atoms spatially. And so we can get sub-nanometer spatial resolution with this type of microscope. And as I was mentioned before by Charles and Frank, we can also generate single cycle terahertz pulses in our lab. These pulses have a time duration of around 1 picosecond. And what we can do is we can shine these laser pulses onto the tip of the STM, just like this. And what this will do, it will induce a rapid change in the bias voltage that we have at the STM junction. And so if we look at this plot, before the pulse arrives, we will have a DC bias that is going to be generating a DC current. But when the pulse arrives, it creates this transient voltage that will modulate the bias. And then after some time, it will relax and go back to BDC. I want to mention that the waveform of the fields at the apex of the tip are not exactly the same as the waveform of our terahertz pulses due to the coupling, the antenna coupling of the fields. So that's something I want to talk about more a little bit later. And the other thing I want to highlight is that, as Charles it was already mentioned before, there's a physical limit on how tight we can focus these beams. However, because of this coupling with the tip, the fields get enhanced just at the apex. And that's why we can still have really, really high resolution, and we can overcome the diffraction limit of the terahertz frequencies. And so, again, we can use the terahertz pulses to modulate the bias at the junction. And what's next? What's going to happen? So every sample usually they all have a characteristic IV curve, such as this one, which basically tells us how the sample is going to respond to a certain voltage. So what we can do is we can map out each point on our terahertz pulse or our bias modulation, and we can assume that the sample is going to respond following this curve. And so we can calculate the terahertz induced current that is going to be produced by the terahertz modulation. And so as you can see here, this is going to be the terahertz induced current response, well, the current response. And as you can see, the positive side is way bigger than the negative side, even though the terahertz pulse is almost symmetric. And that's because the IV curve is non-linear. So that means one side is going to be enhanced more than the other. And so something that is really interesting is that for a regular STM, we usually have currents in the order of tens of picoamps, hundreds of picoamps. But it was found that using this technique, we can get peak currents of hundreds of microamps using the terahertz pulses, which is 7 orders of magnitude larger than what we can get in the regular STM. That's something that hasn't been seen before, and I think that's really, really interesting. And so now that we know what's going to be the instantaneous response of the sample, in reality, we cannot use electronic devices to measure this current because they happen so fast, and there's no way to do it with electronic devices. So how can we do it? Even though we cannot see these transients directly, if we look at the integral of this signal, we're going to have a rectified current such as this one. So what we can measure is the difference between these 2 points, and that's going to tell us, that's going to give us the information about the terahertz induced current. And so this technique was first demonstrated by Tyler Cocker in 2013 in Frank Hegmann's lab. And this is the first time that it was done. And so then one more thing that we can do with this system, using exactly the same setup, is if we reduce the bias voltage of the STM so that only the terahertz pulses generate the current, then we say that we are operating in a terahertz driven STM where we only have the terahertz pulses inducing the currents. And so if we compare the regular STM images that we can get with the ones in the terahertz driven STM mode, we can see that they are basically the same. So that means we don't lose any spatial resolution by using the terahertz. We have roughly the same sub-nanometer resolution in this case. So that's one of the advantages of this technique. Another type of experiment that we can do with this setup is we can do optical POM terahertz probe experiments. So for example, in this case, we have our terahertz pulse, and we also have an ultra-fast infrared pulse, which is roughly 10 times shorter than the terahertz pulse. And so we can control the delay between these 2 pulses. So we can basically excite our sample with the infrared pulse, and then we can use the terahertz pulse to probe the dynamics of the carriers, let's say, after the excitation. So that's something that was done also by Tyler Cocker in the lab, where he was looking at indium arsenide nanodots. And as you can see on the first row, if we send the terahertz pulse first, there won't be any excitation of the sample. So if we look at the terahertz induced current, it's 0 everywhere. But then again, if we change the delay such that the infrared pulse arrives first and it pumps the sample, then on the terahertz channel, we see this image of the nanodot, which was excited by the infrared pulse. So you can imagine that we're taking basically snapshots at different times of the excitation. So if we put all of those snapshots together, we could potentially create a movie of how the carrier, how the sample gets excited and then relaxed. It's easier said than done, but that's one of the potentials of the system. In the lab, we're also doing simulations to corroborate that the results that we get experimentally match the theory. And so we use constant multiphysics for the simulations. And we are trying to study how the terahertz fields propagate in space and how they interact with the geometry of the tip and the sample. And we're doing that because we want to know how the fields evolve in space around the tip apex. Because as I mentioned before, the fields that we get in the near field are not exactly the same as the waveform of the terahertz pulses. So we're using these kind of tools to study that and to have better understanding of what's going on in the system. And so recently, we also developed another a model where we consider the 3D geometry of the tip and the sample to try to predict and explain some of the experimental results that we got in a copper sample. And we found that this model that we built, the simulations results, they match what we measure experimentally, both for the STM and for the terahertz STM systems. And we also use this model to quantify the transient voltages at the apex. And finally, another.
Sorry, Jesus, I'm going to give you your 2-minute warning.
Thank you.
Thanks.
Yeah, I'm almost. Very quickly, another kind of experiment that we can do is where we basically retract the tip, and we can do the same thing as the POM probe. We photoexcite the tip, and then we can use the electron photoemission from the tip to study the near field waveforms from the tip. And so this is just to compare how the terahertz pulses are different to the near fields that we measure at the apex of the tip. We also have an ambient terahertz STM system that we designed and built ourselves, and we can use it to change tips and samples rapidly, and we can also use it with organic samples. And with that, I will conclude my presentation.
Wow, that was really fascinating, Jesus. Just to ask a really naive question. So what samples do you need for these STM type measurements? Or alternatively, what samples just don't work?
We need a conductive sample. So we can do semiconductors and metals. As long as it's conductive, it will work.
Okay, that's really awesome. Do you need any special preparation methods or?
Not really. Well, it depends. For example, in the case of the silicon case, in order to get that surface reconstruction, we need to process the samples. But it really depends on the kind of sample that we want to look at.
Okay, and what next? What sample would you love to actually work on?
I'm really interested in carbon nanotubes. I want to see how they get excited and the relaxation times of the carriers and all that.
Actually, that would be amazing because, of course, there are lots of places there where if the structure isn't perfect, carriers get trapped. So that would be, I think, a fascinating study.
Yeah, and the advantage is that we can look at single nanotubes, not like solutions.
Oh, of course, yeah. So that's great. I think we'll end the session now. Okay, so that concludes this fantastic research showcase. Thanks again to Frank Hegmann, Charles, and Jesus for sharing their terahertz expertise. I was blown away. So now I'd like to reintroduce you to your conference co-chair, Kate Fenwick from the University of Ottawa, to give the closing remarks of the conference. Thank you very much.
Thanks, Amy. And I just want to say a big thanks to each and every one of you for attending this first ever Canadian Photonics online meetup. I really hope you enjoyed today's events, and it was really exciting for me and for ORAD to see so many people on the stream and to see GatherTown in action. Yeah, honestly, really, really cool. So I hope you enjoyed. We have a lot of individuals and organizations to thank for making today possible. First, we want to acknowledge the generous financial support of the Center for Research in Photonics at the University of Ottawa, so the CRPUO, and the Joint Center for Extreme Photonics at the University of Ottawa and the National Research Council of Canada, so JCEP. And combined, their funding has covered the full cost of hosting this conference, making it entirely free for all of you participating. So yeah, a big thank you goes out to them. We also want to acknowledge support from CMC Microsystems, Science Atlantic, Nano Canada, and student chapters from the INRS, l'École Polytechnique Montréal, U Ottawa, and Laval for, among other things, promoting our conference and assisting with the French translations on our website. And finally, a big, big thank you to my co-chair, Orad Reshef, without whom this event really would not have been possible, and to each of our canPOM organizers, Amy Stevens, Ziliang Yi, Andrew Cameron, Danielle Tokars, Richard Sisek, Peter Rostocky, Paul Barclay, and Kathleen McGarvey. They have put in countless hours to ensure today's success, and it truly does not go unnoticed. And with that, I'm going to pass us over to Orad, who will give the final remarks of the closing remarks. Here he is.
Okay, thank you for that, Kate. We really do have to thank Kate Fenwick also for this. If it wasn't for her, this wouldn't happen. I had no desire to do this, and Kate Fenwick was really the bright light to make us all come together and do this. So thank you, Kate. So before we introduce our final event of the day, I just want to take a second to mention that the original Photonics online meetup is hosting yet another worldwide version of POM. It's going to be in January. It's POM 2021 January meeting. If you're interested in attending, please register. It's all free. More information can be found on the POM website, so it's photonicsonlinemeetup.org. And finally, if you are interested in presenting a showcase session or contributing a poster or having a booth at the next canPOM, or if you want to help organize, just please reach out to us directly, especially if you are located in Quebec. We would really like some Quebecers to help us organize this because we're having a lot of trouble finding some. So please just reach out to me or to Kate directly or to anybody on the committee, and we'll talk. So with that, we are excited to introduce our final event of the day. This is our conference dinner. We will be closing down the YouTube stream. So everything will be taking place on GatherTown at the moment. So you should be looking in your email to find your GatherTown link, and you can get on from there. I highly encourage you all to go there right now and to go to the auditorium in GatherTown if you're not already there anyway. So we're going to have a nice evening of networking, trivia, and lively discussions. And now I will pass the baton over to Richard Sisek, who will be running the conference dinner in GatherTown. So thank you very much to everybody, and I hope to be hearing from you all. We are going to be sending out a survey in the coming days. Please fill it in. Things that worked, things that didn't work. We're doing this for you, and so if you can help us make it better, we'll all be the better for it. So thank you all very much, and have a good afternoon. Good night.